Hello there and welcome. Tonight I want to take you somewhere special, somewhere beyond the gentle glow of your bedside lamp, beyond the soft sounds of the evening settling around you, beyond even the familiar boundaries of our small spinning world. Tonight, we're going to drift together into the vast, quiet expanse above us, where silence reigns supreme and mysteries float like dust motes in an endless cathedral of darkness. Settle back into your pillows, let your breathing slow, and allow me to share with you a story that begins not with answers, but with a question that has been quietly circling in my mind like a comet around a distant star. You know, there's something profoundly peaceful about looking up at the night sky and realizing that most of what happens out there happens in complete silence. No sound carries through the vacuum of space, no whispers between the stars, no cosmic conversations that we can hear with our ears, and yet perhaps that's exactly why we should be listening more carefully, not with our ears but with our instruments, our mathematics, our imagination. Because sometimes, just sometimes, the universe sends us visitors that seem to carry messages we're only beginning to learn how to read. Tonight, I want to tell you about one such visitor, a comet that appeared in our skies with a name that sounds almost like a greeting, 3I Atlas. Now, I know what you might be thinking as you lie there in the comfortable darkness. Another comet story. Haven't we seen countless comets come and go, these dirty snowballs tumbling through space, following their predictable orbits, putting on their little shows of light and ice before disappearing back into the cosmic deep? And you'd be right to think that, in a way. We have indeed catalogued thousands upon thousands of comets, watched them brighten and fade, tracked their paths with increasing precision. But what if I told you that this particular comet, this specific visitor from the outer reaches of our solar system, might have been something more than just another chunk of ice and rock? What if its journey to our cosmic neighborhood and the peculiar way it behaved once it got here was not random at all, but perhaps, just perhaps, a gentle test of our awareness, our technology, our readiness to notice things that don't quite fit the expected patterns? It's a question that might sound far-fetched at first, maybe even a little silly as you drift there in the quiet of your room. But as we explore this possibility together over the next few hours, as we examine the evidence and consider the implications, you might find yourself wondering if perhaps we've been looking at cosmic visitors all wrong. Maybe some of them aren't just passive wanderers following the grooves of gravity. Maybe some of them are something more intentional, more purposeful, though not in any threatening or alarming way. Think of it more like a cosmic knock on the door, a gentle tap to see if anyone's home, if anyone's paying attention. Before we dive deeper into this mystery, though, I want to take a moment to acknowledge something important. These explorations we take together, these journeys into the quiet questions of the cosmos, they exist because of listeners like you who value this kind of gentle contemplation. If you find yourself drawn into this story, if you feel that peaceful curiosity stirring as we wander through these cosmic possibilities, I'd like to invite you to consider supporting this channel. Your support, whether through a simple subscription or by sharing these nighttime journeys with others who might enjoy them, helps ensure that we can continue to explore these quiet mysteries together. Think of it as contributing to a kind of cosmic library, a collection of peaceful wanderings that anyone can access when they need to step away from the noise of the day and into the tranquil depths of space. But for now, just relax, just listen, and let's continue our journey together. The story of 3I Atlas begins, as many cosmic stories do, with someone looking up. It was December 28th, 2019, a date that probably passed without much notice for most of us here on Earth. Perhaps you were finishing up the holiday season, putting away decorations, making plans for the new year ahead. But somewhere in Hawaii, at the Mauna Loa Observatory, an automated telescope system was doing what it does every clear night, scanning the sky, taking image after image, looking for anything that moves against the fixed backdrop of stars. This system, called ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, wasn't specifically looking for comets that night. It was doing its regular job of watching for potentially hazardous asteroids, those chunks of rock that occasionally wander too close to Earth for comfort. But on that particular night in that particular patch of sky, the system noticed something. It was faint, incredibly faint, just a tiny smudge of light that hadn't been there in previous images. The automated systems flagged it, as they do with any new discovery, and soon human eyes were examining the data. What they found was a comet, but not just any comet. This one was special for several reasons that would only become clear as we watched it approach the Sun over the following months. They designated it C2019Y4, though it would come to be known more commonly as Comet Atlas, named after the survey that discovered it. The initial calculations of its orbit were exciting, to say the least. If the predictions held true, this comet was going to put on quite a show. Some estimates suggested it might become as bright as Venus in our night sky, maybe even visible during the day. For those of us who love to watch the heavens, this was thrilling news. We hadn't had a really spectacular comet visible from Earth in quite some time, and Atlas seemed poised to break that drought. But even in those early days of discovery, there were hints that this comet was unusual. Its orbit, for instance, was remarkably similar to that of the Great Comet of 1844, suggesting that both might be fragments of a much larger comet that broke apart centuries or even millennia ago. Imagine that for a moment. Somewhere in the deep past, perhaps when the pyramids were being built, or when the first cities were rising from the Mesopotamian plains, a massive comet split into pieces, and we were about to see one of those ancient fragments return home. As January 2020 turned to February and February to March, astronomers around the world turned their instruments toward Atlas. Both professional observatories and amateur astronomers began tracking its progress, measuring its brightness, analyzing the spectrum of its light to understand its composition. The comet was behaving exactly as expected, growing brighter as it approached the Sun, developing a beautiful green coma from the diatomic carbon being released as the Sun's heat began to work on its frozen surface. Everything seemed to be proceeding according to the well-understood physics of cometary behavior. You might wonder, lying there in the darkness, why I'm spending so much time on what seems like a fairly standard comet discovery. After all, we discover new comets all the time, don't we? And you're right, we do. But I want you to really feel the normalcy of those first few months, the comfortable predictability of it all. Because it's only when we understand how normal everything seemed at first that we can fully appreciate the strangeness of what happened next. Picture yourself as one of those astronomers in early 2020, perhaps working from home as the world began to grapple with a very different kind of visitor, a microscopic one that would change all our lives. You're looking at the data coming in from Atlas, watching its brightness curve, planning your observations for the coming weeks. The comet is right on track to become a beautiful naked-eye object by May. You're excited, maybe even making plans to photograph it, to share this cosmic spectacle with friends and family who rarely look up at the night sky. The brightness of a comet, you see, depends on several factors. There's its size, of course, the actual physical dimensions of its nucleus. There's its composition, what kinds of ices and dust it contains. There's its distance from the Sun, which determines how much energy it's receiving to drive the sublimation of those ices. And there's its distance from Earth, which affects how bright it appears to us. All of these factors were looking favourable for Atlas. It was going to pass relatively close to the Sun, about 37 million kilometres at its closest approach, well inside the orbit of Mercury. This would really turn on the fireworks, so to speak, causing massive outgassing and creating a spectacular tail. But then, in late March 2020, something unexpected began to happen. The comet's brightness, which had been steadily increasing exactly as predicted, began to level off. At first, this wasn't too concerning. Comets can be unpredictable after all. They sometimes go through periods of more or less activity as different regions of their surface are exposed to sunlight, or as particularly volatile pockets of ice are exhausted. Professional and amateur astronomers noted the change but remained optimistic. Perhaps this was just a temporary pause before an even more dramatic brightening. However, by early April, it became clear that something more significant was occurring. The comet wasn't just pausing in its brightening, it was actually beginning to fade, and not just fading but changing in appearance. Through telescopes, observers could see that the previously compact, well-defined coma was becoming elongated, stretched out. It was as if the comet was coming apart at the seams, very gently, very quietly, like a dandelion head releasing its seeds into a cosmic wind. This is where our story takes its first really intriguing turn. You see, comets do sometimes fragment. It's not unheard of. The stresses of approaching the sun, the uneven heating, the gravitational forces, they can all contribute to a comet breaking apart. We've observed it happening before with other comets. But there was something about the way Atlas fragmented that was peculiar. Something that even now, as you lie there listening to my voice, makes me wonder if we witnessed something more than just a random cosmic accident. The fragmentation of Atlas wasn't violent or sudden. It was almost graceful, methodical even. Images from the Hubble Space Telescope, which was trained on the comet in April 2020, showed that the nucleus had broken into at least 30 separate pieces, all drifting apart slowly, maintaining a surprisingly organized formation as they continued on their orbit around the sun. It was like watching a flower bloom in extreme slow motion, petals opening and separating but still maintaining a recognizable pattern. Now, I want you to consider something as you drift there in the peaceful darkness. What if this fragmentation wasn't a failure or an accident? What if it was the plan all along? I know it sounds strange, perhaps even a bit fantastical, but stay with me. Imagine for a moment that you wanted to test another civilization's ability to detect and track objects in space. You wouldn't want to send something threatening, something that might provoke a fearful response. You'd want to send something that appeared natural, expected even. But that would reveal, through careful observation, that it was anything but random. Think about the timing of Atlas's appearance and fragmentation. It arrived just as humanity's ability to detect and track near-Earth objects was reaching new levels of sophistication. The very system that discovered it, Atlas, had only been fully operational for a few years. We had recently demonstrated our ability to not just track asteroids and comets, but to actually reach out and touch them, with missions like OSIRIS-REx visiting asteroid Bennu and Japan's Hayabusa 2 visiting asteroid Ryugu. We were even beginning to test our ability to deflect asteroids, with missions like DART being planned to deliberately impact an asteroid to change its orbit. In this context, the arrival of Comet Atlas takes on a different character. It appeared just bright enough to be detected by our automated systems, followed a path that would bring it close enough to Earth to be easily observed but not so close as to pose any threat, and then, just as the entire astronomical community was watching, it performed this elegant fragmentation, almost as if it was putting on a show, demonstrating something to anyone who was paying attention. But demonstrating what, exactly? Well, that's where we need to dive deeper into the nature of comets themselves, to understand what makes them tick, what forces act upon them, and what the specific details of Atlas's behavior might tell us. Because if we're going to seriously consider the possibility that this comet was something more than it appeared, we need to understand what it appeared to be in the first place. So let me take you now on a journey backward in time and outward in space, to the very edge of our solar system, to a realm so distant and so cold that the sun appears as nothing more than a particularly bright star. This is the domain of the Oort cloud, the theoretical home of long-period comets like Atlas, a sphere of icy bodies surrounding our solar system like a vast frozen shell. It's a place that no spacecraft has ever visited, that no human eyes have ever seen directly, but that we know must exist because of visitors like Atlas that occasionally fall from its distant reaches toward the warmth of the inner solar system. The Oort cloud, if you can picture it in your mind's eye, extends from about 2,000 astronomical units from the Sun to perhaps as far as 100,000 astronomical units. An astronomical unit, just to give you a sense of scale, is the distance from Earth to the Sun, about 150 million kilometers. So we're talking about a region that begins far beyond the orbit of Neptune and extends nearly halfway to the nearest star. It's a realm of almost unimaginable emptiness and cold, where the temperature hovers just a few degrees above absolute zero, and where the icy bodies that populate it drift in slow, million-year orbits, barely bound to our Sun's gravity. These bodies, these potential comets, are thought to be remnants from the formation of our solar system 4.6 billion years ago. They're the leftover building blocks, the pieces that didn't get incorporated into planets or moons, frozen preserves of the primordial material from which everything in our solar system formed. In a very real sense, they're time capsules carrying within their icy hearts the chemical signatures of our solar system's birth. But here's where things get interesting from the perspective of our mystery. The Oort cloud isn't just a static repository of ancient ice, it's a dynamic system, constantly being perturbed by passing stars, by the gravitational tide of the galaxy itself, by forces we're only beginning to understand. Every now and then, one of these perturbations is strong enough to nudge an icy body out of its stable orbit and send it falling toward the Sun. This is how long-period comets are born, through a cosmic game of gravitational billiards that can take millions of years to play out. Now, conventional wisdom tells us that this process is entirely random. A star passes by at just the right distance, its gravity tugs on the Oort cloud, and some small percentage of the icy bodies there get displaced. Most of them probably get ejected from the solar system entirely, flung off into interstellar space. But a few, a very few, get nudged in just the right way to begin that long fall toward the Sun. It's all supposed to be chance, cosmic dice rolling in the darkness. But what if it isn't always random? What if sometimes, just sometimes, the trajectory of a comet is chosen rather than chance? I'm not suggesting that every comet is somehow artificial or directed. That would be absurd. The vast majority are undoubtedly exactly what they appear to be, ancient chunks of ice and rock following the laws of physics. But what if, mixed in among these natural wanderers, there are occasional visitors that are something more? Consider the precision required to send an object from the Oort cloud to the inner solar system. You'd need to calculate not just the initial trajectory, but also account for the gravitational influences of all the major planets, the subtle effects of solar radiation pressure, the tiny perturbations from asteroids and other small bodies. It would be like trying to hit a moving target from a distance of thousands of kilometers with a bow and arrow, while blindfolded in a hurricane. The fact that we see comets at all is something of a miracle of celestial mechanics. But if you had sufficient technology, sufficient understanding of orbital dynamics, sufficient patience, you could, in principle, select a specific comet and nudge it onto a specific path. You could time its arrival, control its approach, maybe even engineer its composition or structure to behave in particular ways under particular conditions. It would be the ultimate long-term project, taking potentially millions of years from initiation to completion. But for a civilization that had mastered interstellar travel or communication, what would a few million years matter? This brings us back to Atlas and its peculiar characteristics. Remember, this comet appeared to be related to the Great Comet of 1844, suggesting they were both fragments of a larger body that broke apart long ago. But what if that original fragmentation wasn't natural either? What if it was the first stage of a multi-generational experiment or test, with different fragments programmed, for lack of a better word, to arrive at different times, to test different aspects of our detection and response capabilities? The Great Comet of 1844 arrived when humanity had only the most basic telescopic capabilities. We could see it, marvel at it, but we couldn't analyze its composition, couldn't track its precise orbit, couldn't do much more than watch it pass by. Atlas, on the other hand, arrived when we had space telescopes, spectrometers, automated detection systems, and the ability to model cometary behavior with sophisticated computer simulations. Same family of objects, vastly different human capabilities to observe them. And then there's the matter of that fragmentation. As I mentioned earlier, the way Atlas came apart was unusual. Most comets that fragment do so because of thermal stress or rotational forces. The sun heats one side more than the other, causing uneven sublimation of ices, which can create jets that spin the comet faster and faster until it flies apart. Or thermal cycling causes cracks to propagate through the nucleus until it splits. These processes typically result in a few large fragments and a cloud of smaller debris. But Atlas broke into at least 30 distinct pieces, all of relatively similar size, all separating at relatively similar speeds. The Hubble images showed these fragments arranged almost like a string of pearls, maintaining their formation even as they drifted apart. It was as if the comet had been pre-scored, designed to come apart in exactly this way when it reached exactly this distance from the Sun. Now, you might be lying there thinking that I'm reading too much into what could be natural phenomena, and you'd be absolutely right to maintain that skepticism. Science progresses through skepticism, through demanding evidence, through considering the simplest explanation first. And the simplest explanation for Atlas is certainly that it was a normal comet that happened to fragment in an unusual, but not impossible way. But science also progresses through imagination, through asking what if, and following those questions wherever they lead. And the what if I'm asking tonight is this: what if Atlas was designed to test not our defensive capabilities in a military sense, but our awareness, our scientific sophistication, our ability to notice and interpret subtle anomalies in cosmic visitors? Think about it from the perspective of an advanced civilization trying to assess the technological development of Earth. You wouldn't want to send something obviously artificial. That would contaminate the test. You'd want to send something that appeared natural but contained subtle clues that would only be noticed by a civilization that had reached a certain level of scientific understanding. The fragmentation pattern could be one such clue. The timing of the arrival could be another. The specific orbit, so similar to a previous comet, could be yet another. It's like a cosmic intelligence test hidden in plain sight. Only a civilization that was carefully tracking comets, analyzing their compositions, modeling their behavior, and comparing them to historical observations would notice the patterns. And even then, the patterns would be subtle enough that they could be dismissed as coincidence, maintaining the ambiguity that would be essential for such a test. This isn't as far-fetched as it might sound. We humans have actually considered similar approaches for our own attempts at interstellar communication. The Voyager Golden Records, the Arecibo message, the various SETI protocols we have developed, they all grapple with the same fundamental question. How do you communicate with or test the capabilities of a civilization when you share no common language, no common cultural references, possibly no common biology or even chemistry? One answer is that you use the language of the universe itself, physics, mathematics, patterns that any sufficiently advanced civilization would recognize. A comet following a precisely calculated orbit, fragmenting in a mathematically elegant pattern, arriving at just the right moment in a civilization's technological development, these could all be elements of such a universal language. But let's pull back from speculation for a moment and return to what we actually observed. After Atlas fragmented in April 2020, the individual pieces continued on their orbit toward the Sun. They passed perihelion, their closest approach to the Sun, on May 31, 2020. By this time, they had faded far below naked eye visibility. What had promised to be a spectacular comet visible to everyone had become a target only for large telescopes and dedicated observers. The fragments continued to fade as they moved away from the Sun, eventually becoming too faint to track even with our best instruments. The last observations were made in late 2020, and then Atlas, or what remained of it, disappeared back into the darkness from which it came. The individual fragments are presumably still out there, continuing on modified orbits that will take them back to the outer solar system, perhaps never to return, or perhaps to return in thousands or millions of years as separate comets, with their own stories to tell. In the end, Atlas gave us something different from what we expected, but perhaps something more valuable. Instead of a bright comet to inspire the general public, it gave us a mystery to ponder, a puzzle to solve, a reason to question our assumptions about the nature of cosmic visitors. It reminded us that even in an age of sophisticated technology and comprehensive sky surveys, the universe can still surprise us. The data collected during Atlas's approach and fragmentation has been analysed and reanalyzed by scientists around the world. Papers have been published about its composition, its fragmentation mechanics, its orbital characteristics. The consensus view is that it was a fairly typical long-period comet that happened to be structurally weak and couldn't withstand the stresses of approaching the Sun. Case closed, mystery solved, nothing to see here. But consensus isn't always truth, and the absence of evidence isn't evidence of absence. The possibility I'm inviting you to consider tonight, as you drift towards sleep, is that maybe, just maybe, we witnessed something more than a simple cometary fragmentation. Maybe we witnessed a test, a gentle probe of our capabilities, a cosmic tap on the shoulder to see if we were paying attention. And if that's true, if Atlas was indeed some kind of test or probe, then the next question becomes, did we pass? The fact that we detected it, tracked it, analysed it, and collected extensive data on its fragmentation suggests that we did, at least partially. We showed that we're watching the skies, that we're capable of detecting and studying objects that approach our planet, that we're developing the kind of situational awareness that any spacefaring civilization needs. But perhaps the test went deeper than just detection. Perhaps it was also testing our interpretation, our ability to recognize patterns, to question anomalies, to imagine possibilities beyond the conventional. In that sense, the test might still be ongoing. Every time someone like me wonders about the true nature of Atlas, every time a scientist re-examines the data looking for something they might have missed, every time you lie in the darkness and ponder the possibilities, the test continues. This brings me to one of the most profound aspects of this whole story. Whether or not Atlas was actually designed to test our defenses, the mere possibility that it could have been changes how we think about our place in the cosmos. It reminds us that we're not just passive observers of cosmic phenomena, but active participants in a universe that might be far more aware and intentional than we've assumed. For most of human history, we've looked at comets as omens, as signs from the gods, as harbingers of doom or fortune. Then, with the rise of modern science, we reimagined them as simple physical objects, dirty snowballs following predictable orbits, beautiful but ultimately mundane. But what if the truth is somewhere in between? What if some comets are indeed messages or tests or probes, just not in the mystical sense our ancestors believed, but in a technological sense we're only beginning to be able to conceive? As you continue to relax there in the darkness, letting these ideas wash over you like gentle waves, I want to take you deeper into the cosmic context that makes this possibility so intriguing. Because Atlas didn't arrive in isolation. It came at a particular moment in human history, a moment when we're rapidly developing the technologies and capabilities that would make us detectable to other civilizations, a moment when we're beginning to venture beyond our home planet, a moment when we're starting to take our first tentative steps toward becoming a truly spacefaring species. Think about how much has changed just in the last century. 100 years ago, we had barely begun to understand the true nature of comets. We didn't know about the Oort cloud, didn't understand the mechanisms of cometary tails, couldn't track orbital paths with any real precision. We were still debating whether the canals on Mars were signs of an alien civilization. The universe was a much smaller, much more mysterious place. Now, we have robots on Mars, probes visiting asteroids and comets, telescopes that can see to the edge of the observable universe. We've detected thousands of planets orbiting other stars, some of them potentially habitable. We've begun to map the large-scale structure of the cosmos, to understand our place in a vast web of galaxies and dark matter. We've even started to seriously plan for the defense of our planet against asteroid impacts, with projects like the Atlas system that discovered our mysterious comet. This rapid advancement would be visible to any civilization monitoring Earth from afar. The sudden bloom of radio emissions starting in the early 20th century, the nuclear flashes of atomic tests in the mid-20th century, the growing constellation of satellites in Earth orbit, the probes we've sent to other planets, all of these would be detectable signs of a technological civilization emerging on the third planet from the Sun. And if you were an advanced civilization watching this emergence, wouldn't you be curious? Wouldn't you want to know more about this new technological species, about their capabilities, their intentions, their level of awareness? But how would you investigate without revealing yourself, without contaminating the natural development of this emerging civilization? One way would be exactly what we've been discussing, sending probes disguised as natural phenomena, tests disguised as cosmic accidents, messages hidden in the noise of normal celestial mechanics. It would be a way to gather information while maintaining what we might call the cosmic prime directive, the principle of non-interference with developing civilizations. This concept isn't new to human thought. Science fiction writers have been exploring these ideas for decades. Arthur C. Clarke's Rendezvous with Rama imagined an artificial object passing through our solar system, testing our ability to investigate and understand it. Carl Sagan's Contact explored how an advanced civilization might send messages hidden in mathematical constants or cosmic phenomena. These stories resonate with us because they touch on a deep truth. The universe is vast and old enough that if other intelligences exist, they've had plenty of time to develop capabilities we can barely imagine. But let's bring this back to Atlas specifically. One of the most intriguing aspects of its story is how it intersected with a very human drama that was unfolding at the same time. Remember, Atlas was discovered in December 2019 and fragmented in April 2020. This was exactly the period when the COVID-19 pandemic was emerging and spreading around the world. While astronomers were watching this comet approach and fragment, the rest of humanity was dealing with a very different kind of visitor, a microscopic one that would change all our lives. It's a strange coincidence, isn't it? Or perhaps it's not a coincidence at all. Perhaps the timing was deliberate, a test of whether we could maintain our scientific vigilance, our skywatching capabilities, even in the midst of a global crisis. And remarkably, we did. Despite lockdowns and social distancing, despite the enormous challenges of the pandemic, astronomers continued to track Atlas, continue to collect data, continue to do the work of understanding this cosmic visitor. The Hubble Space Telescope, which provided some of the best images of Atlas's fragmentation, was operated remotely by scientists working from their homes. Amateur astronomers, isolated in their backyards, continued to point their telescopes at the comet and share their observations online. The global astronomical community came together virtually to discuss and analyze what they were seeing. It was, in its own way, a triumph of human cooperation and dedication in the face of adversity. If Atlas was indeed a test, then this response would have been part of what was being tested. Not just our technological capabilities, but our resilience, our ability to maintain long-term projects and observations even when faced with immediate crises. A civilization that can keep watching the stars even when dealing with a pandemic is a civilization that has achieved a certain level of stability and sophistication. But there's another layer to this timing that's worth considering. The pandemic forced many of us to slow down, to spend more time at home, to contemplate our place in the world and the universe. It was a time of reflection for many, a time when the big questions seemed more pressing than ever. In that context, a comet that promised to be spectacular, but instead gently came apart, might have been exactly the kind of cosmic event we needed. Not a dramatic spectacle to distract us, but a quiet mystery to ponder. As we move deeper into our exploration of this possibility, I want to shift our focus from the comet itself to the broader system that detected it, the Atlas system, the Asteroid Terrestrial Impact Last Alert System, is itself a fascinating development in human capability. It consists of 4 telescopes, 2 in Hawaii, 1 in South Africa, and 1 in Spain, that scan the entire visible sky multiple times each night, looking for moving objects that could potentially impact Earth. The system is remarkably sensitive, able to detect objects as faint as magnitude 19, which is about 100,000 times fainter than what the human eye can see. It can spot a 100-meter asteroid several weeks before potential impact, giving us time to calculate its exact trajectory and, if necessary, take action. It's part of a growing network of ground and space-based systems designed to give us comprehensive awareness of what's moving through our cosmic neighborhood. Think about what this represents from a cosmic perspective. A species that was confined to a single continent just a few thousand years ago, that only developed telescopes a few hundred years ago, that only understood the true nature of asteroids and comets in the last century, has now built a planetary defense system. We've gone from cowering in fear at the sight of a comet to actively monitoring, cataloguing, and preparing to deflect potential threats. It's an extraordinary transformation in a cosmically brief period of time, and this transformation hasn't gone unnoticed by our own scientists and philosophers. Many have pointed out that developing planetary defense capabilities is likely a crucial step for any civilization hoping to survive long term. Asteroid impacts are one of the few natural disasters that can cause global extinction. As the dinosaurs learned 66 million years ago, a civilization that can't defend itself against asteroids is unlikely to survive long enough to become truly spacefaring. So when Atlas, the comet, was discovered by Atlas, the detection system, it was more than just a routine discovery. It was a demonstration of a capability that marks a significant milestone in human development. We showed that we're not just passive victims of cosmic forces, but active participants with the ability to detect, track, and potentially respond to objects approaching our planet. If we allow ourselves to imagine that Comet Atlas was indeed some kind of test or probe, then this detection becomes even more significant. It would mean that the test was specifically designed to be discoverable by our current level of technology, not so bright that it would have been easily visible to ancient astronomers, not so faint that it would have escaped our current detection systems, but right in the sweet spot that would require exactly the kind of automated, systematic sky surveys we've recently developed. The name coincidence is interesting too, isn't it? The comet Atlas, discovered by the Atlas system. In Greek mythology, Atlas was the titan who held up the sky, bearing the weight of the heavens on his shoulders. It's a fitting name for a system designed to watch the heavens for threats to Earth, and an intriguing coincidence that the comet would share this name. Or perhaps it's not a coincidence at all. Perhaps it's another layer of the message, a subtle nod to human mythology and meaning-making. But let's not get too carried away with pattern-seeking. Our brains are wired to find patterns, sometimes even where none exist. It's entirely possible that all of these coincidences and anomalies are just that, coincidences. The universe is vast and complex enough that unlikely things happen all the time. The challenge is distinguishing between meaningful patterns and random noise, between signals and static. This is, in fact, one of the central challenges in the search for extraterrestrial intelligence. How do we distinguish between natural phenomena and artificial signals? How do we recognize a message when we don't know what form it might take? These questions have plagued SETI researchers for decades, and they're directly relevant to our consideration of Atlas. The approach most SETI researchers take is to look for things that nature doesn't typically do. Prime number sequences, for instance, or narrowband radio emissions, or regular pulses that don't match any known natural phenomenon. But what if the messages are more subtle? What if they're designed to look natural at first glance, only revealing their artificial nature upon closer inspection? This would actually be a very sensible approach for an advanced civilization trying to make contact or conduct surveillance. By mimicking natural phenomena, they avoid causing panic or disruption. By embedding subtle anomalies, they create a filter that only allows detection by civilizations that have reached a certain level of scientific sophistication. It's like a cosmic IQ test, where passing requires not just technology, but also curiosity, careful observation, and open-mindedness. The fragmentation of Atlas could be seen in this light. Comets do fragment naturally, so the basic phenomenon wouldn't immediately scream artificial, but the specific pattern of fragmentation, the number and size distribution of the fragments, the timing and location of the breakup, these details could contain information for those equipped to read it. Imagine you're an advanced civilization wanting to test Earth's detection and analysis capabilities. You select a comet from the Oort cloud, perhaps one that's already partially fractured or that you've modified in some way. You calculate its trajectory precisely, ensuring it will arrive at Earth at just the right time, when human technology has advanced to a specific level. You engineer it to fragment in a particular pattern that encodes information. Perhaps the number of fragments corresponds to a mathematical constant, or their size distribution follows a specific formula, or their separation velocities encode a message in binary. To most observers, it would just look like a comet breaking apart. But to a civilization sophisticated enough to measure and analyze these parameters precisely, patterns might emerge. The message wouldn't be, "Hello, we're aliens," but rather something more subtle, more ambiguous, more deniable. Just enough to make scientists scratch their heads, to plant a seed of possibility, to encourage further observation and analysis. And this brings us to an important point about the nature of such tests or probes. They wouldn't necessarily be about immediate communication or contact. They might be part of a much longer process, a gradual introduction to the idea that we're not alone, that the universe is more inhabited and intentional than we've assumed. Each ambiguous event, each mysterious visitor, each unexplained phenomenon could be part of a slow acclimation process, preparing humanity psychologically and culturally for eventual contact. Think about how our attitudes toward extraterrestrial life have evolved just in the last few decades. When Orson Welles broadcast War of the Worlds in 1938, it caused panic because many people believed Earth was being invaded. Today, the discovery of microbial life on Mars or Europa would be exciting but not panic-inducing. We've been culturally prepared through science fiction, through scientific discoveries, through a gradual expansion of our cosmic perspective. Perhaps events like Atlas are part of this preparation, not dramatic enough to cause panic, not clear enough to constitute proof, but intriguing enough to keep us thinking, wondering, watching. Each event expands our conceptual framework a little bit, makes us a little more ready for whatever revelations might come next. As you lie there in the darkness, feeling yourself beginning to drift, I want you to consider one more aspect of this story. Whether or not Atlas was designed to test our defenses, thinking about it in this way changes how we see ourselves and our future. It reminds us that we're at a crucial juncture in our development as a species, transitioning from a single-planet civilization to something more. The technologies we're developing to detect and track objects like Atlas aren't just about defending against space rocks. They're about developing situational awareness on a cosmic scale. They're about taking responsibility for our own survival and evolution. They're about becoming active participants in the cosmic community, whether or not that community includes other intelligences. Every telescope pointed at the sky, every spacecraft sent to explore other worlds, every algorithm designed to detect anomalies in astronomical data, these are all steps toward a future where humanity is truly at home in the universe. And maybe, just maybe, events like Atlas are gentle encouragement from others who've already taken these steps, subtle signs that we're on the right track, that we're being watched and, in some cosmic sense, rooted for. The fragments of Atlas are still out there, continuing their journey through the solar system. Some may return in thousands of years as separate comets. Others may be ejected from the solar system entirely, becoming interstellar travelers carrying with them the remnants of whatever message or test they might have embodied. And new comets will come, as they always have, each one a potential mystery, a possible message, a chance to learn something new about the universe and our place in it. As we prepare to move deeper into our exploration, To consider the broader implications of what we've discussed, I want you to hold on to this feeling of peaceful curiosity. The universe doesn't require us to have all the answers. In fact, it's the questions that make life interesting, that drive us forward, that connect us to something larger than ourselves. Whether Atlas was a natural comet or something more, it served its purpose. It made us look up, it made us wonder, and it reminded us that we're part of a vast, beautiful, mysterious cosmos that still has surprises in store for us. Now, let's journey even further back, to the very birthplace of comets like Atlas, to understand the deep history and cosmic context that make such visitors possible. Close your eyes if you haven't already, take a deep breath, and let me tell you about the great river of comets that surrounds our solar system, a frozen reservoir of ancient memories waiting to fall toward the light. The great river of comets, as I like to think of it, isn't really a river at all, of course. It's more like a vast spherical ocean of ice and rock, surrounding our entire solar system in a shell so enormous that light itself takes years to cross it. This is the Oort cloud, named after the Dutch astronomer Jan Oort, who first proposed its existence in 1950, though he was building on ideas that went back even further, to Estonian astronomer Ernst Öpik in 1932. Isn't it remarkable how recent our understanding of this ancient structure is? Your grandparents lived in a world where humanity didn't even know this vast reservoir existed, and now here we are, talking about it as casually as we might discuss the ocean that surrounds an island. But the Oort cloud is nothing like any ocean on Earth. Imagine, if you will, a sphere perhaps 2 light years across, filled not with water, but with countless chunks of ice and rock, each one separated from its neighbours by millions upon millions of kilometres. If you were somehow transported to the Oort cloud right now, you wouldn't see a glittering field of comets. You'd see nothing. Darkness. The profound emptiness of deep space, with the sun appearing as merely the brightest star in a sky full of stars. The nearest comet nucleus might be as far from you as Earth is from the sun, invisible in the darkness, and the next one might be twice that distance away. This is one of the most counterintuitive things about the Oort cloud, and indeed about space in general. When we talk about clouds or swarms or fields of objects in space, we imagine them the way they're depicted in movies, dense collections of rocks or ice that you have to dodge and weave through. But the reality is emptiness on a scale that our Earth-evolved brains simply can't properly comprehend. The Oort cloud contains perhaps trillions of objects larger than a kilometre across, and yet the space between them is so vast that you could fly through it for millions of years and never come close to hitting anything. These objects, these proto-comets as we might call them, have been out there since the very beginning of our solar system. When the sun first ignited 4.6 billion years ago, when the planets were still forming from the swirling disk of gas and dust that surrounded our young star, these icy bodies were there too, forming in the cold outer reaches where water and other volatiles could freeze solid. But they didn't stay where they formed. Through a complex dance of gravitational interactions with the giant planets, especially Jupiter and Neptune, many of these objects were flung outward, exiled to the dark frontier where they've remained ever since. Think about that for a moment. Every comet that falls from the Oort cloud toward the sun is a piece of our solar system's original construction material, preserved in deep freeze for billions of years. When we see a comet like Atlas, we're literally looking at matter that predates Earth itself, that existed before life began, before the oceans formed, before the moon was born from a cosmic collision. These are the most ancient artifacts accessible to us, older than any rock on Earth, older than any meteorite we've ever found. The Oort cloud is like a library of our solar system's history, but it's a library where the books only occasionally fall off the shelves and tumble toward us where we can read them. And what causes these ancient volumes to fall? The gentle gravitational tugs of passing stars, the tidal forces of the galaxy itself, perhaps even the influence of undiscovered planets in the far outer solar system. It's a slow, patient process. A star passes within a light year or two of the sun, which happens every 100,000 years or so, and its gravity ever so slightly perturbs the orbits of Oort cloud objects. Most of these perturbations are tiny, insignificant, but occasionally one is just enough to destabilize an orbit that has been stable for billions of years. The mathematics of this process are fascinating and surprisingly delicate. An object in the Oort cloud is barely bound to the sun's gravity. It's like a ball balanced on top of a hill, needing only the slightest push to start rolling. A passing star doesn't need to come particularly close or be particularly massive to provide that push. Even the combined gravitational effect of the entire galaxy, what we call the galactic tide, can be enough to send comets tumbling inward. Once an object begins its fall from this Oort cloud, its journey to the inner solar system can take millions of years. This isn't a quick plunge, but a slow, graceful spiral, with the comet's orbit gradually tightening as it falls deeper into the sun's gravitational well. Along the way, it passes through different regions of space, each with its own characteristics and hazards. There's the scattered disk, a region of icy bodies beyond Neptune. There's the Kuiper belt, home to Pluto and countless other frozen worlds. There are the giant planets, whose gravity can dramatically alter a comet's path, sometimes sending it right back to the Oort cloud, sometimes ejecting it from the solar system entirely, and sometimes, just sometimes, directing it toward the inner solar system where we wait, watching. This is the conventional story of how comets like Atlas make their way from the Oort cloud to our neighborhood. It's a story of chance and chaos, of random perturbations and unpredictable outcomes. But as I've been suggesting, what if this story, at least sometimes, has another layer? What if the journey of some comets is less random than it appears? Consider the precision required to send a comet from the Oort cloud to a specific point in the inner solar system at a specific time. The calculations would be staggering, requiring not just knowledge of the current positions and velocities of all the major bodies in the solar system, but also predictions of where they'll be millions of years in the future. You'd need to account for relativistic effects, for the pressure of sunlight, for the gravitational influence of asteroids, for the gradual evolution of planetary orbits over geological timescales. It would be one of the most complex calculations imaginable. But for a sufficiently advanced civilization, such calculations might be routine. We humans have only been doing orbital mechanics for a few decades, and already we can send spacecraft on complex trajectories that use gravitational assists from multiple planets to reach their destinations. We can land rovers on Mars, put orbiters around Saturn, and send probes to rendezvous with comets and asteroids. Given a few thousand or million years of technological development, calculating and executing the trajectory of a comet from the Oort cloud might be no more difficult than we currently find calculating the trajectory of a spacecraft to Mars. And if you could do such calculations, if you could nudge Oort cloud objects onto specific trajectories, what would you do with that capability? One possibility, as we've been exploring, is that you might use it to send probes or tests to developing civilizations disguised as natural comets. But there might be other purposes as well. You might use comets as a kind of interstellar communication system, encoding messages in their orbits, their compositions, their behaviors. You might use them to deliver resources or technology, hidden within what appears to be natural ice and rock. You might even use them as a kind of cosmic art, creating beautiful displays for other civilizations to observe and appreciate. The Oort cloud itself might be more than just a natural reservoir of comets. What if some advanced civilization has been using it as a kind of cosmic warehouse, seeding it with objects designed for specific purposes? The cloud is so vast, so dark, so cold, that artificial objects placed there could remain undetected for millions or billions of years. They would be perfectly preserved in the deep freeze of space, waiting for the right moment to be activated or directed toward their targets. This might sound like pure science fiction, but consider that we humans have already started thinking along similar lines. There have been serious proposals to use the Oort cloud as a resource base for future interstellar missions. harvesting water and other volatiles from comets to fuel spacecraft traveling to other stars. Some futurists have even suggested that advanced civilizations might build megastructures in the Oort cloud, taking advantage of the abundant raw materials and the isolation from the inner solar system. If we can imagine such possibilities after just a few decades of space exploration, what might civilizations millions of years older than ours have actually accomplished? The Oort cloud could be teeming with activity that we simply can't detect from Earth. There could be automated systems out there, quietly monitoring the comets, occasionally adjusting their orbits, sending selected objects on carefully calculated trajectories for purposes we can only guess at. This brings us back to the question of detection and visibility. One of the paradoxes of searching for advanced civilizations is that the more advanced they are, the harder they might be to detect. A truly advanced civilization might be able to hide its activities so well that they appear indistinguishable from natural phenomena. Their probes might look exactly like comets. Their communications might be encoded in cosmic rays or gravitational waves or some other natural-seeming phenomenon. Their very presence might be hidden in the patterns of nature itself. This is sometimes called the nature mimicry hypothesis in discussions of extraterrestrial intelligence. The idea is that advanced civilizations might deliberately make their activities look natural to avoid detection by less advanced civilizations, or simply as a matter of efficiency and aesthetics. Why build obviously artificial structures when you can achieve the same goals using modified natural objects? Why broadcast obvious signals when you can encode information in phenomena that already exist? From this perspective, the Oort cloud becomes even more interesting. It's a perfect hiding place, a perfect staging area, a perfect source of raw materials and camouflage. Any civilization capable of interstellar travel would almost certainly pass through their own Oort cloud equivalent on their way to other stars. They would learn to use these resources to navigate these dark regions, to perhaps appreciate the value of these cosmic borderlands. And if multiple civilizations have developed in our galaxy over its billions of years of history, then the Oort clouds of different star systems might overlap or interact in complex ways. Objects could be exchanged between systems, carrying information or materials or even life itself from one star to another. The comets we see might not all be native to our solar system. Some might be interstellar travelers, captured by our sun's gravity after journeying for millions of years through the void between stars. We've actually detected a few objects that we know came from outside our solar system. Oumuamua in 2017 and Borisov in 2019 were both confirmed interstellar visitors, objects with trajectories that indicated they came from other star systems. Oumuamua in particular showed some unusual characteristics that led some scientists to speculate about whether it might be artificial, though the consensus remains that it was probably a natural object, albeit an unusual one. But what if objects like Oumuamua and Borisov are just the tip of the iceberg? What if there are many more interstellar visitors hiding in our solar system, disguised as ordinary comets and asteroids? Some might have been captured by the sun's gravity long ago, and are now indistinguishable from native objects. Others might be passing through on trajectories that will take them back to interstellar space. And some, perhaps, might be artificial probes or messages, waiting to be discovered and decoded. The challenge is that we've only recently developed the ability to detect and track these objects systematically. The Atlas system that discovered our comet, along with other surveys like Pan-STARRS and the upcoming Vera Rubin Observatory, are giving us our first comprehensive view of what's moving through our solar system. We're like people who've lived our entire lives in a house, and are only now starting to systematically catalogue everything in the attic and basement. We're bound to find surprises, and perhaps that's exactly what Atlas was, a surprise that was meant to be found at exactly this moment in our development. Not too early, when we wouldn't have the tools to detect and analyse it properly. Not too late, when such discoveries might be routine. But right at the moment when we're developing the capability to defend our planet from impacts, to track objects throughout the solar system, to begin thinking seriously about our cosmic future, The timing is particularly intriguing when you consider the broader context of human development. We're at what many futurists call a crucial century, or a hinge of history. The decisions we make in the next few decades about artificial intelligence, genetic engineering, climate change, and space exploration could determine the entire future trajectory of our species. We're developing capabilities that could lead to our extinction or our expansion throughout the cosmos. We're at a branching point where the paths diverge dramatically. In such a context, a gentle test or probe from an advanced civilization makes perfect sense. They wouldn't want to interfere directly to push us down one path or another, but they might want to observe, to assess our capabilities and our choices, to perhaps provide subtle hints or encouragement. A comet that behaves slightly unusually, that makes us think and wonder and question, could be exactly the right kind of intervention, significant enough to matter, subtle enough not to disrupt. As you continue to drift there in the peaceful darkness, feeling the weight of your body settling into rest, I want you to imagine the Oort cloud as it might appear to an advanced civilization. Not as a cold, dead reservoir of ice, but as a garden of possibilities, a library of information, a workshop of cosmic engineering. Each comet is a seed that might bloom into something beautiful or meaningful when it falls toward the light. Each trajectory is a carefully composed line of poetry, written in the language of orbital mechanics. Each fragmentation is a flower opening its petals to reveal hidden messages or purposes. This perspective transforms our understanding of comets from simple astronomical objects to potential carriers of meaning and intention. Every comet that graces our skies becomes a possible messenger, a potential test, a maybe probe from the vast intelligence that might permeate the cosmos. We don't need to believe that all comets are artificial or directed to appreciate this possibility, even if only 1 in a million comets is something more than it appears. That's still potentially thousands of subtle contacts over the history of our solar system. And this brings us to a profound realization about the nature of cosmic intelligence and communication. Perhaps the universe is already full of messages and signals and probes, but they're hidden in plain sight, camouflaged as natural phenomena. Perhaps the distinction between natural and artificial breaks down at sufficiently advanced levels of technology. Perhaps the entire cosmos is in some sense bound a living system of information and intention, with comets and asteroids and planets all playing roles in a vast, slow conversation that we're only beginning to perceive. The fragments of Atlas continue their journey through the solar system as we speak, or as we rest, I should say. They're out there right now, in the darkness between the planets, following their modified orbits, carrying with them whatever secrets they might hold. Some pieces might still be outgassing slightly, leaving faint trails of vapor that glow briefly in the sunlight before dissipating into the vacuum. Others might be completely dormant now, indistinguishable from small asteroids, waiting for their next approach to the sun to reactivate them. Each fragment is now on its own trajectory, its own journey through time and space. They might never reunite, these pieces of what was once a single body. They'll drift apart over the centuries and millennia, their orbits diverging more and more until they bear no resemblance to each other. Some might be perturbed by Jupiter or Saturn and sent on entirely new paths. Others might maintain relatively stable orbits for millions of years, and perhaps 1 or 2 might eventually fall back to Earth, not as visible comets, but as meteorites, carrying with them the physical evidence of their strange fragmentation. Imagine if, decades or centuries from now, we found one of these fragments. By then, our technology might be advanced enough to analyze it in ways we can't even imagine today. We might be able to read its entire history and its isotope ratios, its crystal structure, its embedded cosmic ray tracks. We might find anomalies that don't quite fit our models of cometary formation and evolution. We might find patterns or structures that suggest something else. Or we might find nothing unusual at all, just ordinary cometary material water ice and dust and organic molecules, the same stuff we've found in every comet we've studied. And that would be fine too. The mystery doesn't require resolution to be valuable. Sometimes the questions are more important than the answers, the journey more meaningful than the destination. As we prepare to move into the next phase of our exploration, to look more closely at Atlas's specific journey and behaviour, I want you to carry with you this sense of the vast, patient processes that brought it to us. Whether it fell from the Oort cloud by chance or by design, it travelled for millions of years to reach us. It crossed billions of kilometres of empty space, passed by the giant planets, survived the increasing heat of the sun, all to arrive at just the moment when we were watching, when we were ready to see it and study it and wonder about it. In the grand scheme of cosmic time, our observation of Atlas was less than a blink, a momentary intersection of paths that had been converging for eons. We happened to be here, happened to be looking, happened to have the tools to see it. Or perhaps happened is the wrong word. Perhaps it was always going to be this way, written into the initial conditions of its orbit millions of years ago. Perhaps someone or something knew we would be here, knew we would be watching, knew we would wonder. The Oort cloud continues its slow rotation around the sun, its trillions of objects pursuing their patient orbits in the darkness. Right now, as you rest, other comets are beginning their long falls toward the sun. Some won't arrive for millions of years. Others might appear in our skies next year or next decade. Each one will bring with it a piece of that primordial library, a fragment of frozen history, a possible message from the deep, and we'll be watching. Our telescopes scan the sky every night. Our computers analyze the data. Our scientists stand ready to investigate anything unusual. We've become the watchers, the guardians, the interpreters of cosmic visitors. It's a responsibility we've taken on without fully realizing it, a role we've assumed as naturally as we once assumed the role of hunters, or farmers, or builders. Perhaps that's what Atlas was really testing. Not our specific technologies or capabilities, but our readiness to take on this role, to be conscious participants in the cosmic community. And if that's the case, then I think we can say we passed the test, at least the first phase of it. We saw it coming, we watched it carefully, we documented its strange behaviour, and we're still thinking about what it might mean. But the test, if that's what it was, isn't over. It continues every time we look at the sky, every time we detect a new comet or asteroid, every time we ask ourselves whether we're alone in the universe. The test is ongoing, and we're all participants, including you, lying there in the darkness, contemplating these possibilities, adding your consciousness to the collective human awareness that watches and wonders and waits. Now, let's turn our attention to that first moment of discovery, that winter night in 2019 when Atlas first appeared in our instruments, a faint smudge of light against the cosmic dark, carrying with it the promise of spectacle and the seeds of mystery, a faint green glow. That's all it was at first, barely distinguishable from the background noise of the universe, a whisper of light that had travelled for years to reach the electronic sensors of a telescope perched high on a Hawaiian mountain. December the 28th, 2019 was ending, those liminal days between Christmas and New Year when the world seems to pause, catching its breath between one year and the next. Most of humanity was focused on earthly concerns, holiday celebrations, family gatherings, resolutions for the coming year. But the Atlas telescope system never rests, never pauses, never takes a holiday. It continues its patient vigil, scanning the sky in an endless search for objects that move against the fixed tapestry of stars. The telescope that detected our comet that night wasn't operated by a lonely astronomer pulling an all-night shift, peering through an eyepiece in a cold dome. Those romantic days of astronomy are largely behind us now. Instead, the discovery was made by sophisticated software, algorithms trained to identify the telltale signs of a moving object in a series of images. The system takes multiple exposures of the same patch of sky, minutes apart, and then compares them, looking for anything that has shifted position. Stars remain fixed, galaxies stay put, but asteroids and comets betray themselves through their motion. When the software flagged this particular object, it assigned it a temporary designation based on the date and order of discovery. It would later receive its official name, C2019Y4, Atlas. But in those first moments, it was just another blip, another data point, another possible threat to Earth that needed to be tracked and analysed. The system automatically calculated a preliminary orbit based on its position and motion, and this is where things got interesting. The orbit was long, very long. This wasn't a near-Earth asteroid on a short loop around the Sun. This was a visitor from the deep, a long-period comet falling in from the outer darkness. The initial calculation suggested an orbital period of about 6,000 years, meaning the last time this object had been in the inner solar system, humans were just developing the first cities in Mesopotamia. The pyramids hadn't been built yet. Writing had barely been invented, and now it was returning, right on schedule, to a world transformed beyond recognition. But there was something else about the orbit that caught astronomers' attention. It bore a striking resemblance to the orbit of the Great Comet of 1844, one of the most spectacular comets of the 19th century. That comet had been visible in broad daylight, its tail stretching across a significant portion of the sky. The similarity in orbit suggested that both comets might be fragments of a much larger parent body that had broken apart during a previous passage through the inner solar system. Think about that for a moment. Somewhere in the deep past, perhaps 5,000 years ago, perhaps 50,000, a massive comet had approached the Sun and split into pieces. Each piece continued on a similar but slightly different orbit, spreading out over time like runners in a very slow, very long race. The Great Comet of 1844 was one piece, Atlas was another, and there might be more pieces out there, still approaching, still waiting for their turn to fall toward the Sun. This connection to the Great Comet of 1844 immediately made Atlas more interesting to both professional and amateur astronomers. If it was indeed a sibling of that spectacular comet, it might put on a similar show. Early brightness measurements were encouraging. The comet was still far from the Sun, out beyond the orbit of Mars, but it was already showing signs of activity. A fuzzy coma had formed around its nucleus, indicating that solar heating was beginning to sublimate the ices, even at that great distance. The colour of the coma was particularly striking, a beautiful green glow caused by diatomic carbon molecules fluorescing in sunlight. This green colour is common in comets, but it never fails to captivate observers. There's something almost otherworldly about it, a colour that seems to belong more to the realm of fantasy than reality. In photographs, Atlas appeared like a tiny emerald against the black velvet of space, a jewel falling slowly toward the Sun. As January 2020 progressed, more and more telescopes turned toward Atlas. The astronomical community operates on a principle of open data sharing, especially for potentially hazardous objects or spectacular events. Observations from around the world were compiled, refined orbital calculations were made, and brightness predictions were updated. The excitement began to build. Based on its current rate of brightening, Atlas might become visible to the naked eye by May, possibly reaching magnitude 5 or brighter, making it one of the brightest comets in decades. The media began to pick up the story. Comet Atlas could be the brightest comet in decades, the headlines proclaimed. Amateur astronomers started making plans for observation and photography. Star parties were scheduled, equipment was prepared. There was a palpable sense of anticipation in the astronomical community. We were about to get a front row seat to one of nature's most spectacular shows. But even in those early optimistic days, there were signs that Atlas might not behave as expected. Its rate of brightening was unusual, faster than most models predicted for a comet of its size and composition. This could mean one of two things. Either the comet was larger than initially estimated, or it was unusually active, releasing more gas and dust than typical for its distance from the Sun. Some astronomers warned that such rapid brightening could be a bad sign. Comets that brighten too quickly sometimes do so because they're falling apart, exposing fresh ice to sunlight and creating a temporary surge in activity. It's like a piece of ice cream taken out of the freezer on a hot day. It might look spectacular as it melts, but the show doesn't last long. Still, optimism prevailed through February and into March. Atlas continued to brighten. Now visible through binoculars and small telescopes, its coma expanded, growing to several times the diameter of Jupiter as seen from Earth. The tail began to develop, a faint stream of gas and dust blown back by the solar wind. Everything seemed to be proceeding toward a spectacular climax in May. It was around this time that I first became deeply interested in Atlas. I remember standing in my backyard one clear March evening, binoculars in hand, searching for the comet among the stars of Ursa Major. When I finally found it, a fuzzy green dot barely distinguishable from the stars around it, I felt that familiar thrill of cosmic connection. Here was an object that had been travelling for thousands of years to reach this moment, and I was witnessing its approach, adding my observations to the thousands of others being made around the world. There's something profoundly moving about observing a comet. Unlike the stars, which appear eternal and unchanging on human timescales, comets are dynamic, ephemeral. They change from night to night, week to week. They're visitors, travellers, storytellers from the outer reaches of our solar system. Each one is unique, with its own composition, its own behaviour, its own story to tell. As I observed Atlas over those weeks in March, I began to notice something that the brightness measurements were also showing. The comet's rate of brightening was starting to level off. It wasn't as dramatic at first, just a slight deviation from the expected curve, but it was there. The comet that had been brightening faster than expected was now brightening slower than expected. Something was changing. Professional astronomers were noticing the same thing, and speculation began about what might be happening. Was the comet running out of volatile ices to sublimate? Had it rotated to expose a less active region to sunlight? Or was something more fundamental happening to its structure? The only way to know for sure was to keep watching, to gather more data, to let the comet reveal its secrets in its own time. This is one of the beautiful things about astronomy. It teaches patience. We can't hurry cosmic events. We can't fast forward to see how things turn out. We have to wait, watch, and accept the universe on its own terms and timescales. Atlas was going to do whatever it was going to do, regardless of our hopes or expectations. All we could do was bear witness. By late March, more sophisticated instruments were being trained on Atlas. The Hubble Space Telescope, despite being busy with numerous other observations, was scheduled to take a look. Ground-based telescopes with adaptive optics were pushing the limits of their resolution, trying to see details in the comet's coma and nucleus. Radio telescopes were listening for emissions from various molecules in the comet's atmosphere. It was a full-court press of astronomical observation, and then, in early April, the first signs of fragmentation became visible. It wasn't dramatic at first, just a subtle elongation of the nucleus, as if the comet was stretching. But to experienced comet observers, this was an ominous sign. Elongation often precedes fragmentation, like cracks appearing in a dam before it breaks. I remember the night I first saw the elongation through my telescope. It was April 5th, 2020, a Sunday evening. The world was in the grip of the growing pandemic, lockdowns were being implemented, and the future seemed uncertain in so many ways. But the sky was clear, the stars were bright, and Atlas was there, faithful to its orbital appointment. When I focused on it through my 8-inch reflector telescope, I could see that something had changed. The previously round, compact coma now looked stretched, pulled out of shape like a piece of taffy. Over the next few nights, the elongation became more pronounced. What had been one object was clearly becoming multiple objects, though they were still close together, still travelling as a group. It was like watching a slow-motion explosion, if explosions could be gentle and graceful rather than violent and chaotic. The Hubble observations from April 20th and 23 confirmed what ground-based observers were seeing. Atlas had fragmented into multiple pieces. The images were stunning in their clarity, showing at least 4 major fragments and numerous smaller ones, all surrounded by a cloud of dust and gas. The comet hadn't exploded so much as it had come apart at the seams, like a snowball gently crumbling in warm hands. The fragmentation of Atlas was both a disappointment and an opportunity. A disappointment because it meant the comet wouldn't become the spectacular naked-eye object we'd hoped for. The fragments, being smaller than the original nucleus, couldn't sustain the same level of activity. The comet began to fade, its show ending before the final act. But it was also an opportunity because cometary fragmentations are relatively rare events, and catching one in the act provides valuable scientific data. By studying how Atlas came apart, scientists could learn about its internal structure, its composition, the forces that hold comets together, and the forces that tear them apart. Every fragment was a piece of the puzzle, every observation a clue to the comet's nature and history. The pattern of fragmentation was particularly interesting. Unlike some comets that split into 2 or 3 large pieces, Atlas seemed to be disintegrating more uniformly, breaking into many similarly sized fragments. This suggested that the nucleus might have been a loosely bound collection of smaller bodies rather than a single solid object, what astronomers call a rubble pile structure. This rubble pile hypothesis fits well with our current understanding of how comets form. In the early solar system, small particles of ice and dust would have gently collided and stuck together, gradually building up larger and larger bodies. These bodies wouldn't be solid rocks, but more like dirty snowballs or icy dirt balls, held together by weak forces and their own minimal gravity. Such structures would be particularly vulnerable to the stresses of approaching the sun. But here's where our speculation about Atlas being more than a natural comet becomes interesting again. If you wanted to design an object that would fragment in a specific controlled way, a rubble pile structure would be ideal. You could engineer the connections between the components to fail at specific temperatures or stress levels. You could arrange the components in patterns that would become visible only when the object came apart. You could, in essence, create a 3-dimensional message that would only be readable when the comet fragmented. I'm not saying this is what happened with Atlas. I'm simply pointing out that the observed fragmentation pattern, while consistent with natural processes, is also consistent with intentional design. The ambiguity is perfect, clear enough to make us wonder, vague enough to maintain plausible deniability. It's exactly what you'd expect from a test or probe designed to assess our observational capabilities without revealing its true nature. The fragments of Atlas continued to evolve over the following weeks. Some pieces brightened temporarily as fresh ice was exposed to sunlight. Others faded quickly, exhausting their volatile materials. The entire ensemble spread out along the orbital path, creating what astronomers call a string of pearls effect. It was beautiful in its own way, even if it wasn't the spectacular comet we'd hoped for. By May 2020, when Atlas should have been at its brightest, it had faded below naked-eye visibility. Only telescopes could still track the fragments, and even they were struggling as the pieces continued to disperse and fade. The comet that had promised to light up our skies had instead given us a different kind of show, a demonstration of cosmic fragility, a reminder that not everything in the universe goes according to our plans or expectations. But perhaps that was the message all along. Perhaps Atlas was meant to teach us about impermanence, about the delicate nature of cosmic bodies, about the importance of observing and documenting phenomena while we can because they might not last. If it was a test, maybe it wasn't testing our defensive capabilities so much as our ability to adapt, to learn from unexpected events, to find value in outcomes we didn't anticipate. The scientific papers about Atlas's fragmentation are still being written and published. Each one adds new details, new insights, new pieces to the puzzle. Some focus on the mechanics of the fragmentation, using computer models to simulate how the comet came apart. Others analyze the composition of the fragments, using spectroscopy to identify the molecules released during the breakup. Still others look at the orbital evolution of the fragments, predicting where they'll go and when they might return. One particularly intriguing finding is that the fragments showed slightly different compositions, suggesting that the original nucleus was heterogeneous, made up of materials that formed at different times or in different places. This is like finding that a snowball contains layers of snow from different storms, each with its own unique signature. It tells us that Atlas's history was complex, that it had probably been modified and reformed multiple times over its long life. This heterogeneity could be natural, the result of collisions and mergers in the Oort cloud. Or it could be artificial, the result of deliberate construction or modification. Again, we're in the realm of ambiguity, of possibilities that can't be proven or disproven with our current data. But that's what makes it so fascinating. We're looking at evidence that could be interpreted multiple ways depending on our assumptions and perspectives. As I reflect on the story of Atlas's discovery and fragmentation, I'm struck by how it mirrors the human experience of discovery and disappointment, expectation and surprise. We thought we knew what would happen, but the universe had other plans. We had to adapt, to find meaning and value in an outcome we didn't expect. Isn't that always the way with exploration and discovery? The most interesting findings are often the ones we didn't anticipate, the ones that force us to reconsider our assumptions. The green glow of Atlas has long since faded from our skies, but its impact on our understanding continues. Every comet we observe from now on will be compared to Atlas, its unusual brightening and fragmentation adding to our database of cometary behavior. We'll be better prepared for the next comet that promises great things, more aware that such promises aren't always kept, but that the broken promises can be just as valuable as the kept ones. And perhaps that's the real test. Not whether we can detect and track comets, not whether we can predict their behavior, but whether we can find meaning and value in whatever the universe presents to us. Whether we can maintain our curiosity and wonder, even when things don't go as planned. Whether we can see the beauty in fragmentation, the message in the unexpected, the lesson in the disappointment. As you continue to rest there in the darkness, feeling yourself drifting deeper into that peaceful space between waking and sleeping, I want you to hold on to this image of Atlas as it was in those early days of 2020. A faint green glow against the stars, full of promise and mystery, approaching us from the depths of space and time. It carried with it the hopes and expectations of thousands of observers, the accumulated light of ancient suns, and perhaps, just perhaps, a message we're still trying to decode. The story of Atlas is far from over. Its fragments continue their journey through the solar system, each one carrying a piece of the original mystery. Some may return in centuries or millennia, appearing as new comets to future generations who may not even remember Atlas or understand their connection to it. Others may be lost forever, ejected from the solar system or ground down to dust by the relentless forces of space. But the questions Atlas raised, the possibilities it suggested, the wonder it inspired, these things persist. They've become part of the human story, part of our ongoing dialogue with the cosmos. Every time someone looks up at the night sky and wonders if we're alone, every time a scientist analyzes data looking for patterns that don't quite fit, every time you or I consider the possibility that the universe is more intentional and aware than we have assumed, Atlas lives on. The faint green glow may have faded, but the light it brought to our understanding continues to shine, and perhaps that's enough. Perhaps that's exactly what was intended. A gentle touch, a subtle message, a quiet reminder that we're part of something larger, something mysterious, something wonderful. The cosmos doesn't always shout its secrets. Sometimes it whispers them in the soft green glow of a comet that came to visit and left us with more questions than answers. As we prepare to explore what happened next, to delve into the details of Atlas's fragmentation and what it might mean, let that green glow linger in your mind's eye. Let it be a beacon calling us deeper into the mystery, a gentle light guiding us through the darkness of uncertainty toward whatever revelations await. The journey is far from over. In many ways, it's just beginning. The promise that faded. It's such a human way to describe what happened to Atlas, isn't it? As if the comet had made us a personal commitment, whispered a guarantee across the cosmic void, and then changed its mind. But of course, comets make no promises. They simply follow the laws of physics, responding to heat and gravity, and the fundamental forces that govern all matter. The promise was ours, projected onto a chunk of ice and rock that knew nothing of our hopes and expectations. And yet, as I lie here with you in this quiet moment, I can't help but feel that there was something almost intentional about the way Atlas disappointed us, as if the universe was teaching us a gentle lesson about attachment and impermanence. By the first week of April 2020, it had become clear that something was wrong with Atlas. Wrong isn't quite the right word, actually. Different. Unexpected. The comet that had been brightening so promisingly through January, February and March had begun to stall. Its light curve, that beautiful mathematical expression of increasing brightness that astronomers had been tracking with such excitement, had started to flatten. At first, the change was subtle enough that observers could dismiss it as a temporary fluctuation. Comets, after all, are notoriously unpredictable. They can undergo outbursts that temporarily increase their brightness, or they can have quiet periods where activity subsides. But this wasn't an outburst followed by a return to normal. This was the beginning of something else entirely. I want you to imagine for a moment what it's like to watch something come apart in slow motion. Not violently, not dramatically, but gently, almost peacefully. Like watching a sandcastle being reclaimed by the tide, or a cloud dispersing on a warm afternoon. That's what happened to Atlas over the course of April 2020. The solid nucleus that had survived for perhaps millions of years in the cold darkness of the Oort cloud, that had endured the long fall toward the sun, began to surrender to forces it could no longer resist. The first signs were subtle. Through large telescopes, observers noticed that the previously sharp, concentrated center of the comet's coma was becoming elongated. It was as if someone was gently pulling taffy, stretching what had been a compact ball into an extended shape. This elongation is often a precursor to fragmentation in comets, a sign that the nucleus is beginning to break apart under the stresses of solar heating and its own rotation. But knowing what's likely to happen and watching it actually unfold are two very different experiences. Professional astronomers immediately recognized the significance of what they were seeing. Fragmentation events are relatively rare, and catching one in real time is even rarer. Suddenly, Atlas transformed from a potentially spectacular public spectacle into a scientifically valuable event. Telescope time was hastily rearranged. Observation campaigns were organized. The Hubble Space Telescope, our eye in the sky, was tasked with taking a closer look. What had been a source of public excitement became a source of scientific urgency. The Hubble observations from April 20th, 2020 reveal the truth in stunning detail. Atlas hadn't just elongated, it had shattered. The images showed at least 4 major fragments, each surrounded by its own cloud of dust and smaller debris. But these weren't random chunks flying apart in all directions. The fragments were arranged in a line like pearls on an invisible string, all following essentially the same orbit but slowly drifting apart. It was one of the most organized fragmentations ever observed, almost artistic in its symmetry. This is where our story takes on that additional layer of intrigue I've been hinting at. You see, when comets fragment naturally, they typically do so in one of a few ways. Sometimes they split in two, like Comet Biela did in the 19th century. Sometimes they explode more violently, creating a cloud of debris with a few larger chunks. But Atlas did something different. It came apart into multiple pieces of surprisingly similar size, all separating at remarkably similar velocities. It was as if the comet had been pre-scored, designed to break along specific fault lines when subjected to specific conditions. Now, I'm not saying this is impossible naturally. We know that comets can have complex internal structures with layers and boundaries that could potentially lead to this kind of fragmentation. But the precision of it, the timing of it, the almost choreographed nature of it, makes one wonder. If you were an advanced civilization wanting to send a probe that would reveal its artificial nature only to those sophisticated enough to notice subtle patterns, wouldn't this be exactly the kind of behavior you'd engineer? Think about it from an engineering perspective. You'd want your probe to appear completely natural until a specific trigger point. Maybe that trigger is reaching a certain distance from the sun, experiencing a certain temperature, or being observed with a certain level of scrutiny. At that point, the probe would execute its program, fragmenting in a way that encodes information. The number of fragments, their size distribution, their separation velocities, the pattern of their arrangement, all of these could carry meaning for those equipped to read it. But let's return to what we actually observed, to the facts as we know them. By April 23rd, when Hubble took its second set of images, the fragments had spread out even more. The count had increased to at least 25 distinct pieces, possibly as many as 30. Each fragment was surrounded by its own coma, its own little atmosphere of sublimating gas and dust. Together they created a ghostly procession, a funeral parade for what might have been a great comet. The scientific community responded to this fragmentation with a mixture of disappointment and excitement. Disappointment because the promised spectacle wouldn't materialize. The fragments, being much smaller than the original nucleus, couldn't maintain the same level of activity. The comet that might have been visible in daylight would now require a telescope to see. But there was also excitement because fragmentation events provide unique insights into cometary structure and composition. Each fragment is like a core sample, revealing different layers and components of the original body. Spectroscopic analysis of the fragments showed interesting variations in composition. Some pieces seemed richer in certain organic molecules, others in different types of ice. This heterogeneity suggested that Atlas wasn't a uniform body, but rather a collection of different materials that had come together at some point in the past. It was like discovering that what you thought was a single rock was actually a conglomerate of many different rocks cemented together. This heterogeneity is particularly interesting from our speculative perspective. If Atlas was indeed some kind of artificial probe or test, the different compositions of the fragments could have been intentional, each piece designed to release specific molecules or create specific spectroscopic signatures when heated by the sun. It would be like writing a message in chemistry, readable only by those with the instruments and knowledge to detect and interpret molecular emissions. The timing of the fragmentation is another intriguing aspect. Atlas began to break apart just as it was becoming bright enough to attract widespread public attention, just as amateur astronomers around the world were turning their telescopes toward it, just as the media was beginning to hype it as the comet of a generation. If you wanted to test humanity's ability to observe and document a rapidly changing celestial event, you couldn't have asked for better timing. Maximum eyes on the sky, maximum instruments trained on the target, maximum data collection. And then there's the context of when this happened, April 2020. The world was in the grip of the COVID-19 pandemic. Lockdowns were being implemented globally. People were isolated in their homes, looking for distractions, for connections to something beyond their immediate circumstances. The night sky, for many, became a source of solace. Amateur astronomy experienced a surge in interest as people sought safe, socially distanced activities. Atlas could have been a beautiful shared experience for humanity during a difficult time. Instead, it became something else. a reminder that the universe doesn't conform to our schedules or needs. Or perhaps that was the point. Perhaps the lesson, if there was one, was about resilience and adaptation, about finding meaning and value even when things don't go as planned, about the importance of scientific observation even during times of crisis. The fact that astronomers continue to track and study Atlas throughout the pandemic, that papers continue to be written, that data continue to be collected and analysed, says something profound about human dedication to understanding the cosmos. I remember those April nights vividly. The world felt like it was falling apart, and so was Atlas. There was something poetic about the parallel, something that resonated on a deep level. We were all fragmenting in our own ways, separating from our normal lives, our usual patterns, our expected futures. And yet, like the fragments of Atlas, we continued on our paths, still connected even in separation, still part of a larger whole even as we drifted apart. The fragments continued to evolve through late April and into May. Some pieces brightened temporarily as fresh ice was exposed to sunlight. These outbursts were like death throes, final gasps of activity before the inevitable fade. Other fragments dimmed steadily, their volatile materials exhausted, leaving behind only dark, inactive cores. The entire ensemble spread out along the orbital path, creating a train of debris hundreds of thousands of kilometers long. By May 31st, 2020, when Atlas reached perihelion, its closest approach to the Sun, the show was essentially over. What should have been the comet's moment of maximum glory was instead a whimper. The fragments were too faint for naked eye observation, visible only through telescopes, and even then, they were challenging targets. The comet that had promised to light up our skies had instead become a test of observers' dedication and equipment. But the scientific observations continued. Every fragment was tracked for as long as possible. Every spectrum was analysed. Every image was processed and reprocessed, extracting every bit of information possible. The death of Atlas became one of the most thoroughly documented cometary fragmentations in history. In a way, the comet achieved a different kind of immortality, not as a spectacular sight, but as a valuable scientific case study. The data revealed fascinating details about the fragmentation process. The fragments didn't separate at constant velocities, but showed acceleration patterns that suggested ongoing sublimation jets. Some pieces rotated rapidly, others tumbled chaotically. Some maintained relatively stable comas, others fluctuated wildly in brightness. Each fragment behaved like an individual comet, with its own personality and peculiarities. One particularly interesting observation was that some fragments seemed to fragment further, creating second and third generation pieces. It was like watching a fractal pattern emerge, with breakup at multiple scales. This hierarchical fragmentation suggested that Atlas had a complex multi-scale structure, possibly the result of multiple accretion events in its history. Or, if we allow ourselves to speculate, possibly the result of intentional design, with predetermined breakpoints at different scales. The spectroscopic data was equally revealing. As different fragments heated up and released gas, they showed different molecular signatures. Some were rich in cyanogen, which produces a green glow. Others showed strong emissions from C2, diatomic carbon, or NH2, amidogen. The variation suggested that different parts of the original nucleus had different compositions, like a cosmic layer cake with each layer made of different ingredients. This compositional heterogeneity is actually quite important for understanding how comets form. The traditional view was that comets were relatively uniform bodies, formed from well-mixed material in the early solar system. But Atlas and other recent comet observations suggest a more complex picture. Comets might be amalgamations of materials that formed at different times and places, brought together by gentle collisions in the outer solar system. They're not single entities, but collections, assemblages, temporary alliances of ice and dust. From our speculative perspective, this heterogeneity could serve another purpose. If you were designing a probe to test another civilization's analytical capabilities, you'd want to include a variety of materials that would produce different signatures when analyzed. The fragmentation would then reveal this variety, like opening a box of assorted chocolates. Each piece would tell a different part of the story, and only by observing all the pieces could the full message be understood. As May turned to June, and June to July, the fragments of Atlas continued to fade. One by one, they dropped below the detection threshold of even large telescopes. Some may have completely sublimated away, returning their materials to the interplanetary medium as gas and dust. Others may have exhausted their volatiles and become inactive, dark nuclei continuing on modified orbits. These dead fragments are still out there, invisible and untrackable, ghost ships sailing through the darkness. The last confirmed observation of an Atlas fragment was made in September 2020. After that, the comet that had captured so much attention simply vanished from our instruments. It didn't explode or collide with anything dramatic. It just faded away, like a conversation trailing off, like a song ending on an unresolved note. The promise that had seemed so bright in January had completely faded by fall. But what exactly was that promise? Was it just our human projection onto a natural phenomenon, or was there something more? If we consider the possibility that Atlas was some kind of test or probe, then perhaps the promise was never about providing a spectacular show. Perhaps it was about something else entirely, testing our response to disappointment, our ability to find value in the unexpected, our dedication to observation and understanding, even when the rewards aren't what we anticipated. Think about what humanity demonstrated through the Atlas event. We showed that we could detect faint objects far from Earth. We showed that we could quickly mobilize observational resources when something interesting happened. We showed that we could coordinate observations globally, sharing data and insights across borders and time zones. We showed that we could maintain scientific operations even during a global pandemic. And perhaps most importantly, we showed that we could find scientific value in an event that disappointed public expectations. These are all characteristics of a mature, scientifically capable civilization. We didn't panic when the comet fragmented. We didn't invent wild theories or see omens of doom. We observed, we analyzed, we learned. We turned disappointment into data, failure into knowledge. If this was indeed a test, I'd say we handled it pretty well. The promise that faded also taught us something about the nature of cosmic phenomena. The universe doesn't owe us spectacles. It doesn't arrange itself for our entertainment or convenience. Comets come and go on their own schedules, following their own rules, indifferent to our hopes and expectations. This might seem cold and uncaring, but I find it oddly comforting. It means the universe is bigger than us, older than us, operating on scales and principles that transcend human concerns. And yet, we're part of it. We're made of the same stuff as comets, formed from the same primordial material, governed by the same physical laws. When we observe a comet, we're literally watching our cosmic cousins, seeing materials and processes that gave rise to our planet and ourselves. Every comet that passes through our skies is a reminder of our cosmic heritage and our cosmic context. The fragments of Atlas carried away more than just ice and dust when they dispersed. They carried away a moment in human history, a collective experience of anticipation and disappointment, a shared story that connected observers around the world. Everyone who pointed a telescope at Atlas, everyone who took a photograph or made a measurement, everyone who simply looked up hoping to see it, became part of that story. I was part of it too, and so, in a way, are you, listening to this tale as you drift towards sleep. We're connected through this story to all the other humans who watched and wondered, who hoped and were disappointed, who found meaning in the fragments of a promise that couldn't be kept. It's a very human story, even if the protagonist was a chunk of ice from the edge of the solar system. As we move forward in our exploration, preparing to examine the evidence and speculation surrounding Atlas's true nature, I want you to hold on to this feeling of bittersweet acceptance. The promise faded, yes, but something else emerged in its place. knowledge, wonder, connection, and perhaps a message we're still trying to understand. Not all promises are meant to be kept. Sometimes the broken promises teach us more than the fulfilled ones ever could. The night sky continues its eternal rotation above us, carrying with it new comets yet to be discovered, new promises yet to be made and possibly broken. Atlas is gone, but its legacy remains in the data it provided, the questions it raised, the possibilities it suggested. Every future comet will be compared to Atlas, its fragmentation pattern analyzed in light of what we learned, its behavior interpreted through the lens of this experience. And perhaps that's the real promise that Atlas kept, the promise to make us think, to make us question, to make us look more carefully at the cosmic visitors that grace our skies. It promised to be memorable, and it certainly achieved that, just not in the way we expected. The bright comet we anticipated became instead a mystery, a puzzle, a gentle reminder that the universe still has surprises in store for those who watch and wait and wonder. Reading the dust. When Atlas came apart in April 2020, it left behind more than disappointment. It left evidence, clues written in the language of light and chemistry, dynamics and distribution. Like forensic investigators at a scene, astronomers began the meticulous work of analyzing every fragment, every spectrum, every image, searching for understanding in the debris of a shattered comet. What they found was both exactly what theory predicted and subtly different in ways that continue to puzzle researchers today. As you rest there in the darkness, let me take you through this investigation, this careful reading of cosmic dust that might, just might, contain a message we're only beginning to decipher. The first thing to understand about cometary fragmentation is that it's not actually uncommon. We've observed dozens of comets breaking apart over the years, from the famous Shoemaker-Levy 9 that crashed into Jupiter in 1994, to the more recent fragmentation of Comet Linear in 2000. Each event teaches us something new about the internal structure of these cosmic wanderers, about the forces that hold them together and the forces that tear them apart. But Atlas was special in several ways that made its fragmentation particularly valuable for scientific study. First, there was the timing. We caught Atlas in the act, observing the fragmentation as it happened rather than discovering it after the fact. This allowed astronomers to track the evolution of the fragments from the moment of breakup through their gradual dispersal and fading. It's like the difference between finding scattered puzzle pieces and watching someone take the puzzle apart piece by piece. The dynamic information, the process itself, is just as valuable as the end result. Second, there was the quality of observations. Despite the challenges of the pandemic, or perhaps because people had more time to dedicate to observation, Atlas was monitored by an unprecedented network of professional and amateur astronomers. Telescopes ranging from backyard instruments to the Hubble Space Telescope collected data across the electromagnetic spectrum. We have visible light images, infrared observations, spectroscopic data, polarimetry measurements, and even some radio observations. It's one of the most complete datasets ever assembled for a fragmenting comet. Third, and perhaps most intriguingly, there was the pattern of fragmentation itself. As I mentioned earlier, Atlas didn't just split in two or explode randomly. It came apart in a remarkably organized fashion, producing fragments of similar size that separated at similar velocities. This uniformity is unusual and has led to considerable debate about what it tells us about the comet's internal structure and the mechanism of its fragmentation. Let's dive deeper into what the dust and debris actually revealed. When a comet fragments, it exposes fresh material that may have been buried deep within the nucleus for billions of years. This material immediately begins sublimating in the sun's heat, creating jets of gas and dust that can be analyzed spectroscopically. Each molecule has its own spectral fingerprint, a unique pattern of absorption and emission lines that identifies it as surely as a barcode identifies a product in a store. The spectra from Atlas's fragments showed a rich mixture of molecules. There was water, of course, the primary component of most comets, but there was also carbon monoxide, carbon dioxide, methane, ammonia, and a variety of more complex organic molecules. The presence of these volatiles isn't surprising. We expect to find them in comets. What was interesting was their relative abundances and how they varied between fragments. Some fragments were particularly rich in carbon monoxide, suggesting they came from regions of the nucleus that had remained especially cold since CO sublimes at lower temperatures than water ice. Other fragments showed strong emissions from more complex organics, possibly indicating regions where chemical processing had occurred, either in the early solar system or during the comet's long journey through space. It was as if each fragment was a sample from a different geological layer, each with its own story to tell. The dust itself was equally revealing. As gas escapes from a fragmenting comet, it carries with it tiny particles of dust. These particles scatter sunlight in characteristic ways depending on their size, shape, and composition. By analyzing the scattered light, astronomers can deduce properties of the dust without ever physically collecting it. It's remote sensing at its finest, reading the properties of matter from the way it interacts with light across millions of kilometers. The dust from Atlas showed an interesting size distribution. Rather than the typical power law distribution we see from most comets, where there are many more small particles than large ones, Atlas's dust showed a more unusual pattern. There seemed to be preferred sizes, as if the dust had been sorted or processed in some way. This could be natural, the result of particular formation conditions or subsequent processing, or it could be something else. I want you to consider for a moment what dust might mean to an advanced civilization trying to send a subtle message. Dust particles are incredibly numerous. A single comet can release trillions upon trillions of them. Each particle could, in principle, carry information in its size, shape, composition, or isotopic ratios. The collective properties of the dust, its size distribution, its scattering characteristics, its chemical makeup, could encode complex messages readable only by those with the technology to detect and analyze such properties. We humans have actually considered similar ideas for our own attempts at interstellar communication. There have been proposals to send clouds of smart dust to other star systems, microscopic probes that could spread throughout a planetary system and report back. If we can imagine such things with our current technology, what might a civilization thousands or millions of years more advanced be capable of? But let's return to what we actually observed. One of the most intriguing aspects of Atlas's dust was its color. Different fragments produced dust of slightly different colors, ranging from the typical grey-brown of most cometary dust to unusual reddish and even bluish tints. Color in dust is determined by its composition and the size of the particles. The color variations suggested that different parts of the original nucleus had different mineralogies or had experienced different processing histories. The polarization of light scattered by the dust was another source of information. When light bounces off particles, it can become polarized, with the light waves aligned in particular directions. The degree and angle of polarization depend on the properties of the particles. Atlas's dust showed unusual polarization characteristics, different from most other comets we've studied. The polarization evolved as the fragments aged, suggesting ongoing changes in the dust properties, possibly due to sublimation of ice mantles or fragmentation of the dust particles themselves. The dynamics of the fragmentation, how the pieces moved apart, provided yet another set of clues. In a simple fragmentation caused by thermal stress or rotational breakup, we'd expect the fragments to separate at velocities determined by the energy of the breakup event. But Atlas's fragments showed a more complex pattern. Some pieces seemed to accelerate after the initial breakup, driven by jets of sublimating gas. Others moved in ways that suggested they were still gravitationally bound to each other, at least initially. The arrangement of the fragments was particularly striking. In the Hubble images from late April 2020, the major fragments were arranged almost perfectly along a line, like beads on a string. This linear arrangement persisted for weeks, even as the fragments drifted apart. Such organization is unexpected from a random fragmentation event. It suggests that the breakup occurred along a preferred axis, possibly a pre-existing weakness in the nuclear structure. One hypothesis is that Atlas was a contact binary, two lobes connected by a narrow neck, and that it split along this neck. We've seen other comets with this kind of structure, like Comet 67P Churyumov-Gerasimenko, visited by the Rosetta mission. But the subsequent fragmentation of each lobe into multiple pieces of similar size remains puzzling. It's as if the comet was designed to come apart in stages, first into major sections, then into smaller uniform pieces. The size distribution of the fragments is perhaps the most intriguing puzzle. When we plot the number of fragments versus their size, we don't get the smooth curve we'd expect from a random breakup. Instead, there are preferred sizes, peaks in the distribution that suggest some organizing principle. It's like finding that a shattered window is broken into pieces that cluster around certain sizes rather than showing a continuous range. In physics, such preferred scales often indicate resonances or underlying structural patterns. In the case of Atlas, it might mean that the nucleus had a regular internal structure, perhaps layers or blocks of a characteristic size. Or it might mean that the fragmentation process itself had preferred scales, determined by the balance of forces acting on the nucleus. Or, if we allow ourselves to speculate, it might mean that the fragmentation was controlled, engineered to produce fragments of specific sizes. The chemical evidence adds another layer to the mystery. Isotope ratios, the relative abundances of different versions of the same element, can tell us about the conditions under which materials formed. The deuterium to hydrogen ratio in water from Atlas was similar to other Oort cloud comets, suggesting a common formation environment. But some of the minor isotope ratios showed unusual patterns, slightly different from the typical cometary values. These isotopic anomalies could be explained by various natural processes. Perhaps Atlas incorporated materials that had been processed by cosmic rays during its long residence in the Oort cloud. Perhaps it contained pre-solar grains, particles that formed around other stars before our solar system existed. Or perhaps the anomalies are telling us something else, encoding information in the subtle language of nuclear physics. The organic molecules detected in Atlas's fragments were particularly interesting. Beyond simple molecules like methane and methanol, there were hints of more complex organics, possibly including amino acids and other prebiotic compounds. These are the building blocks of life as we know it, and their presence in comets supports the idea that comets could have delivered the raw materials for life to early Earth. But the distribution of these organics among the fragments was not uniform. Some pieces seemed particularly enriched in complex organics, while others were relatively depleted. This heterogeneity could be natural, reflecting different formation or processing conditions in different parts of the nucleus. But it could also be intentional, with different fragments designed to release different molecular signatures when heated. The temporal evolution of the fragments provided additional clues. Some pieces brightened days or weeks after the initial fragmentation, suggesting delayed activation of fresh surfaces. Others showed periodic variations in brightness, indicating rotation or periodic outgassing. The patterns were complex, seemingly random, yet when analyzed statistically, they showed certain regularities that are still being studied. One particularly intriguing observation was that some fragments seemed to fragment further at specific distances from the Sun, as if triggered by reaching certain temperature thresholds. This cascade fragmentation created a hierarchy of pieces, from the major fragments down to tiny particles. The self-similar nature of this fragmentation, with breakup occurring at multiple scales, is reminiscent of fractal patterns found throughout nature. The velocity distribution of the fragments and dust particles also contained information. In addition to the bulk motion of the major fragments, there was a cloud of smaller particles moving at a range of velocities. When astronomers analyzed this velocity distribution, they found it didn't quite match what models predicted for a simple thermal or rotational fragmentation. There seemed to be preferred velocities, as if the particles had been ejected by a more organized process. Some researchers have suggested that Atlas's fragmentation was triggered by the sublimation of a particularly volatile component, perhaps a pocket of carbon monoxide ice that suddenly vaporized when the comet reached a critical distance from the Sun. This could explain the sudden and relatively uniform nature of the breakup. But it doesn't fully explain all the observed characteristics, particularly the size, distribution and arrangement of the fragments. Others have proposed that Atlas was held together by very weak forces, perhaps just van der Waals forces between loosely aggregated particles, and that even the gentle heating from the Sun was enough to overcome these forces. This would make Atlas one of the most fragile large objects we've ever observed, a cosmic dust bunny that fell apart at the slightest provocation. But again, this doesn't fully explain the organized nature of the fragmentation. The most exotic natural explanation involves the possibility that Atlas contained regions of amorphous ice that underwent a phase transition as it warmed. Amorphous ice, which can form in the extreme cold of the outer solar system, can suddenly crystallize when heated, releasing energy and potentially triggering fragmentation. This process could potentially explain some of the unusual characteristics of Atlas's breakup, though the details remain to be worked out. But what if we step beyond natural explanations? What if the fragmentation of Atlas was not a failure but a feature? What if the comet was designed to come apart in exactly this way, at exactly this distance from the Sun, producing exactly this pattern of fragments and dust? The evidence, while not conclusive, is at least consistent with this possibility. Consider what such a designed fragmentation might accomplish. First, it would test our observational capabilities. Could we detect the fragmentation quickly? Could we mobilize resources to observe it? Could we track multiple fragments simultaneously? Could we analyze the dust and gas in real time? Atlas tested all of these capabilities and we largely succeeded. Second, it would test our analytical capabilities. Could we measure the size distribution of fragments? Could we determine their compositions? Could we model their dynamics? Could we synthesize observations from multiple sources into a coherent picture? Again, Atlas provided a comprehensive test of these abilities, and the scientific community rose to the challenge. Third, and perhaps most importantly, it would test our interpretive capabilities. Could we recognize patterns in the fragmentation? Could we identify anomalies in the data? Could we consider alternative explanations beyond the conventional? Could we maintain scientific rigor while remaining open to possibilities? This test is ongoing, as scientists continue to analyze and debate the Atlas observations. The dust from Atlas is still out there, spreading through the inner solar system. Some of it will eventually fall to Earth, perhaps to be collected by high-altitude aircraft or to settle gently onto Antarctic ice. When we analyze these particles in our laboratories, we might find additional clues, isotopic patterns or mineral structures that tell us more about the comet's nature and origin. But even without physical samples, the dust has already told us a great deal. It's revealed a comet of unusual complexity, with a heterogeneous structure and composition. It's shown us a fragmentation pattern that challenges our models and expands our understanding of how comets can come apart. And it's provided a data set that will be analyzed and reanalyzed for years to come, possibly revealing patterns and messages we haven't yet recognized. As you lie there, drifting deeper into that peaceful space between waking and sleeping, I want you to imagine the cloud of dust from Atlas spreading through the solar system like ink in water, like thoughts dispersing into the cosmic consciousness. Each particle carries information about where it came from and what it experienced. Together they form a kind of distributed memory of the comet, a story written in dust that we're still learning how to read. The reading of this dust is more than just a scientific exercise. It's a conversation between humanity and the cosmos, a dialogue conducted in the language of light and matter, dynamics and chemistry. Whether Atlas was a natural comet or something more, whether its fragmentation was random or designed, The very act of observing and analyzing it connects us to the larger universe. We become part of the story, readers and interpreters of cosmic messages, whether intended or emergent. The evidence from Atlas's dust is like a poem written in an ancient language. We can recognize some words, understand some phrases, but the full meaning remains elusive. Perhaps that's as it should be. Perhaps the mystery is more valuable than any solution could be. Perhaps the questions Atlas raised are more important than any answers it might have provided. As we prepare to delve deeper into the implications of what we've observed, to consider seriously the possibility that Atlas was more than it appeared, remember that we're reading more than just dust. We're reading the story of our solar system, the history of our cosmic neighborhood, and possibly, just possibly, a message from intelligences beyond our current understanding. The dust speaks to those who know how to listen, and we're still learning the language. A question of intent. Now we arrive at the heart of our contemplation, the central mystery that has been threading through our entire journey tonight. Was the behavior of Comet Atlas simply the result of natural forces acting on a fragile body of ice and rock? Or was there something more deliberate, more intentional about its approach and fragmentation? As you rest there in the comfortable darkness, feeling yourself drifting ever deeper into that twilight space between consciousness and dreams, let me guide you through this delicate question, this possibility that transforms everything we've discussed from a simple astronomical event into something far more profound. Intent is such a human concept, isn't it? We look for it everywhere, in the behavior of animals, in the patterns of weather, in the arrangements of stars. Our brains are wired to detect agency, to distinguish between things that happen and things that are done. It's a survival mechanism that served our ancestors well. The rustle in the bushes might be just the wind, or it might be a predator. Better to assume intent and be wrong than to miss a real threat. But this same tendency can lead us to see intent where none exists, to project consciousness onto unconscious processes, to find messages in random noise. So when I ask whether Atlas's behavior showed intent, I'm aware that I'm walking a fine line between legitimate speculation and wishful thinking. The scientific method demands that we consider the simplest explanation first, and the simplest explanation for Atlas is that it was a normal comet that behaved in unusual but ultimately natural ways. Occam's razor, that powerful tool of logical thinking, suggests we shouldn't multiply entities unnecessarily. If natural processes can explain what we observed, then that's what we should accept. But here's the thing about Occam's razor. It's a guideline, not a law. Sometimes the simplest explanation isn't the correct one. Sometimes the universe is more complex, more interesting, more intentional than we assume. And sometimes the evidence, while not conclusive, points toward possibilities that challenge our assumptions about what's natural and what's designed. Let's consider what intentional design might look like in the context of a comet. If an advanced civilization wanted to send a probe to our solar system, why disguise it as a comet? The answer, when you think about it, is elegant in its simplicity. Comets are expected. We see them all the time. They don't cause panic or major disruption. They follow predictable orbits governed by well-understood physics. A probe disguised as a comet could observe us without triggering defensive responses or cultural upheaval. It's the perfect camouflage. But more than that, a comet-like probe would test specific capabilities that might interest an advanced civilization assessing our technological development. Can we detect objects approaching from the outer solar system? Can we calculate their orbits precisely? Can we analyze their composition remotely? Can we coordinate observations globally? Can we respond quickly to unexpected changes? These are exactly the capabilities that would indicate a species is ready for the next stage of cosmic awareness. The timing of Atlas's arrival is the first thing that gives me pause. It appeared just as humanity was reaching a critical threshold in our space capabilities. We had recently demonstrated the ability to land on comets and asteroids with missions like Rosetta and OSIRIS-REx. We had developed automated sky surveys capable of detecting faint objects. We were beginning to seriously plan for planetary defense against asteroid impacts. The DART mission to deliberately impact an asteroid was in advanced planning stages. In cosmic terms, Atlas arrived at precisely the moment when we would be able to detect it, track it, and learn from it, but not so advanced that its appearance would be routine. Consider the orbital characteristics. Atlas's orbit was remarkably similar to the Great Comet of 1844, suggesting they were fragments of the same parent body. But what if that parent body's fragmentation wasn't natural? What if it was designed to send multiple probes to Earth at different times, each arriving when humanity had reached a different level of technological sophistication? The Great Comet of 1844 arrived when we could observe it but not analyze it in detail. Atlas arrived when we could do both. Perhaps there are more fragments still coming, time to arrive when we're even more capable. The fragmentation pattern is perhaps the strongest hint of possible intent. As we've discussed, Atlas didn't fragment randomly. It came apart in an organized fashion, producing fragments of similar size arranged in a linear pattern. This could be natural, the result of internal structure and the specific forces acting on the nucleus. But it could also be designed, engineered to fragment in exactly this way, to create a specific pattern, to encode information, or to test our ability to observe and interpret complex events. Think about how you might design such a system if you were an advanced civilization. You'd want the probe to appear completely natural until a specific trigger point. Perhaps that trigger is reaching a certain distance from the sun, experiencing a certain temperature, or detecting certain types of observation from Earth. At that point, the probe would execute its program, fragmenting in a way that reveals its artificial nature, but only to those sophisticated enough to notice the patterns. The number of fragments could encode information. In mathematics and physics, certain numbers have special significance. The fact that Atlas produced approximately 30 major fragments is interesting. 30 is a highly composite number, divisible by 1, 2, 3, 5, 6, 10, 15, and 30. It's the smallest number with exactly 8 divisors. Could this be significant? Or am I reading meaning into coincidence? The size distribution of the fragments showed preferred scales, peaks at certain sizes rather than a smooth distribution. In information theory, such quantization often indicates encoded information. It's like the difference between analog and digital signals. Natural processes typically produce analog distributions, smooth curves. Designed systems often produce digital distributions, discrete values. The size distribution of Atlas's fragments looks more digital than analog, though this could admittedly be due to natural resonances we don't fully understand. The chemical composition of the fragments provides another layer of possible intent. The variations in molecular abundances between fragments could be natural heterogeneity, or they could be designed to create specific spectroscopic signatures when heated. Imagine encoding a message in chemistry, with different fragments releasing different molecules in a pattern that carries meaning. It would be like writing with fireworks, but on a cosmic scale and in the language of spectroscopy. The timing of the fragmentation, just as the comet was becoming bright enough to attract widespread attention, seems almost too perfect. If you wanted maximum observation of the fragmentation event, you couldn't have timed it better. It occurred when the comet was well placed for observation from Earth, when our best telescopes could be brought to bear, when the global astronomical community was watching. It's as if the comet waited until it had our full attention before revealing its true nature. But let's be honest about the weaknesses in this speculation. Every pattern I've pointed out could have a natural explanation. The timing could be coincidence. The orbital similarity to the Great Comet of 1844 could be because they really are natural fragments of the same parent body. The organized fragmentation could be due to internal structure we don't fully understand. The chemical variations could be natural heterogeneity. The preferred sizes could be due to physical resonances in the fragmentation process. This is the challenge of looking for intent in cosmic phenomena. The universe is vast and complex enough that patterns emerge naturally without design. We see faces in clouds, not because clouds are designed to look like faces, but because our brains are designed to recognize faces. Similarly, we might see intent in Atlas not because it was intentional, but because we're primed to look for intent. And yet, the possibility remains. What if some small percentage of the comets we see are not natural? What if there's a kind of cosmic ecology we're not aware of, with artificial objects mixed in among the natural ones? What if advanced civilizations routinely send probes disguised as natural phenomena, maintaining a kind of cosmic surveillance network that monitors developing civilizations? This idea isn't as far-fetched as it might seem. We humans have already considered similar strategies for exploring other star systems. The Breakthrough Starshot project proposes sending tiny probes to nearby stars, accelerated by powerful lasers. These probes would be so small and fast that they'd be virtually undetectable by any civilization that wasn't specifically looking for them. If we can imagine such things with our current technology, what might civilizations millions of years older be capable of? The concept of directed panspermia, the idea that life might be deliberately spread through the galaxy by intelligent beings, has been seriously discussed by scientists including Francis Crick, co-discoverer of DNA structure. If life can be spread deliberately, why not intelligence? Why not messages? Why not tests? The SETI community has long debated what form extraterrestrial signals might take. Radio waves, laser pulses, neutrino beams. But what if the signals are more subtle, embedded in phenomena we think are natural? What if comets, asteroids, even cosmic rays carry information we haven't learned to decode? What if the universe is full of messages, but we're like people who can't read standing in a library? This brings us to the question of motivation. Why would an advanced civilization send camouflage probes to observe us? The answer might be as simple as curiosity. We send probes to other planets just to learn about them, to understand how they work, to see if they harbor life. An advanced civilization might have similar motivations, scaled up to interstellar distances, or the motivation might be more complex. Perhaps they're monitoring us to ensure we don't pose a threat. Perhaps they're waiting for us to reach a certain level of development before making contact. Perhaps they're testing us to see if we're worthy of joining some kind of cosmic community. Perhaps they're studying us the way we study isolated tribes, trying not to interfere with our natural development. The non-interference principle, often called the prime directive in science fiction, might be a real ethical principle followed by advanced civilizations. They might believe that developing civilizations should be allowed to evolve naturally, without external interference, but monitoring would still be necessary to ensure that this principle is being followed, that no one is interfering, that natural development is proceeding. If Atlas was indeed a probe, what information might it have gathered? Through its fragmentation, it would have tested our detection and tracking capabilities. Through our response, it would have measured our scientific sophistication and our ability to coordinate globally. Through our analysis and interpretation, it would have assessed our intelligence and creativity. And through our speculation about its nature, it would have gauged our openness to cosmic possibilities. The probe wouldn't need to transmit this information back to its creators in any conventional sense. The information could be encoded in the trajectories of the fragments, in the dust and gas released, in the subtle perturbations of other solar system bodies. Or perhaps the probe doesn't need to report back at all. Perhaps it's part of a vast network of probes that collectively monitor the galaxy, sharing information through mechanisms we can't yet imagine. One intriguing possibility is that the fragmentation of Atlas was not just a test but also a message. The pattern of fragmentation, the chemical signatures, the dynamics of the event, all of these could encode information intended for us to decode. It might be a kind of cosmic IQ test, with the message becoming readable only to civilizations that have reached a certain level of scientific understanding. What might such a message say? Perhaps something simple, like the prime numbers or mathematical constants that SETI researchers have long looked for. Perhaps something more complex, like instructions for building a communication device or accessing a galactic network. Perhaps something philosophical about the nature of consciousness or the purpose of intelligence in the universe. Or perhaps the message is simply the fact of the probe itself. You're not alone, you're being watched, you're part of something larger. But even if Atlas was entirely natural, the questions it raises about intent and design are valuable. They force us to think about what artificial probes might look like, how we might recognize them, how we might respond to them. They prepare us psychologically and culturally for the possibility that we're not alone, that the universe might be more inhabited and intentional than we've assumed. The search for intent in cosmic phenomena is ultimately a search for meaning, for purpose, for our place in the grand scheme of things. Whether or not Atlas was designed, the fact that we can ask the question, that we can imagine the possibility, that we can look for evidence and evaluate hypotheses, says something profound about human consciousness. We're not just passive observers of the universe, we're active interpreters, meaning makers, storytellers. As you continue to drift towards sleep, feeling the gentle pull of dreams beginning to form at the edges of your consciousness, I want you to hold this question of intent lightly, like a soap bubble that might pop if you grasp it too firmly. The beauty of the question is not in having a definitive answer, but in the wondering itself, in the expansion of possibility it creates in our minds and hearts. Perhaps Atlas was just a comet, following the laws of physics, fragmenting due to natural forces, leaving behind nothing but dust and data. Or perhaps it was something more, a gentle probe from an ancient civilization, a test of our readiness, a message we're still learning to read. The universe is vast enough, old enough, strange enough to accommodate both possibilities and many more we haven't yet imagined. The question of intent transforms how we see every comet, every asteroid, every cosmic visitor that graces our skies. Each one becomes a potential message, a possible probe, a maybe meaningful event in the ongoing dialogue between Earth and cosmos. We don't need to believe that all or even most of these objects are artificial to appreciate the possibility. Even if only 1 in a million is something more than it appears, that's still a universe rich with intention and intelligence. And perhaps that's the real message, whether from Atlas or from our own questioning minds, that we live in a universe where intention is possible, where consciousness can emerge from matter, where beings can look at the stars and wonder if other beings are looking back. The question of intent is ultimately a question about consciousness, about whether mind and purpose are rare accidents or fundamental features of the cosmos. The watchers on the pale blue dot. That's what we are, isn't it? Billions of conscious beings clinging to a small rocky world, orbiting an ordinary star in an unremarkable galaxy. And yet we've developed the audacity to watch the cosmos, to track objects millions of kilometers away, to ask whether we're alone in the vast darkness. When Atlas approached and fragmented in 2020, it didn't just test our technical capabilities, it revealed something profound about what humanity has become in the early 21st century. We're no longer passive victims of cosmic forces. We have become active participants, watchers, guardians of our own small corner of space. And perhaps, just perhaps, that transformation is exactly what something out there was waiting to see. Let me take you back to that pale blue dot for a moment, to see ourselves as Atlas might have seen us, if indeed it was capable of seeing. From the distance of Mars's orbit, where Atlas began its final approach, Earth appears as nothing more than a bright star, slightly bluish, accompanied by an even fainter companion that is our moon. All of human history, every life that has ever been lived, every civilization that has risen and fallen, every love story and tragedy and triumph, all of it contained in that single point of light. Carl Sagan called it a mote of dust, suspended in a sunbeam, and from Atlas's perspective, that's exactly what we were. But what a remarkable mote of dust we've become! In the span of just a few decades, less than a human lifetime, we've transformed from a species that could barely detect approaching comets to one that maintains constant surveillance of the entire sky. The Atlas system that discovered our mysterious comet is just one part of an unprecedented network of eyes that humanity has turned toward the heavens. There's Pan-STARRS in Hawaii, scanning the sky with one of the world's largest digital cameras. There's the Catalina Sky Survey in Arizona, discovering more near-Earth objects than any other survey. There's the newly operational Vera Rubin Observatory in Chile, capable of photographing the entire visible sky every few nights. We've built a planetary detection network that would have seemed like magic to our grandparents. Think about what this represents from a cosmic perspective. A species that evolved to hunt and gather on the African savanna, whose eyes developed to spot predators and find fruit, has repurposed that visual system to detect threats from space. We've extended our vision with silicon sensors and computer algorithms, creating artificial eyes thousands of times more sensitive than our biological ones. We've networked these eyes globally, sharing data across continents in real time, coordinating observations between nations that can't agree on earthly matters but unite in watching the sky. The Atlas system itself is a marvel of human ingenuity and determination. Each telescope is relatively modest by professional standards, just 0.5 meters in diameter. But what they lack in size, they make up for in dedication and sophistication. Every clear night, they photograph the entire sky visible from their locations, taking hundreds of images that are immediately processed by sophisticated software. This software doesn't just look for moving objects, it characterizes them, calculates their orbits, assesses their potential threat to Earth, and alerts astronomers worldwide if something interesting is found. The system can detect a 100-meter asteroid several weeks before it would impact Earth, giving us time to calculate its exact trajectory and, if necessary, take action. It's found hundreds of potentially hazardous asteroids, thousands of main belt asteroids, and dozens of comets. But more than just finding objects, Atlas represents a fundamental shift in how we relate to the cosmos. We're no longer just stargazers. We're cosmic census takers, cataloguing every rock and ice ball that wanders through our neighborhood. When Atlas the Comet was discovered by Atlas the Survey, it was more than just a routine detection. It was a demonstration of this new capability, this transformation of humanity from watch to watcher. If the comet was indeed some kind of probe or test, then this detection was exactly what it would have been designed to measure. Can the inhabitants of Earth detect a relatively faint object approaching from the outer solar system? The answer was unequivocally yes, but detection is just the first step. What happened next revealed even more about our capabilities and our nature as a species. Within hours of discovery, the information about the new comet was shared globally through the Minor Planet Center, an international clearinghouse for astronomical observations. Astronomers around the world turned their instruments toward the new object. Amateur astronomers, alerted through online networks and social media, began their own observation campaigns. The global astronomical community, professional and amateur alike, came together to track and study this visitor from the outer darkness. This level of coordination would have been impossible just a generation ago. The internet, modern telecommunications, and digital imaging have transformed astronomy from a solitary pursuit to a collective endeavor. When I was young, an astronomer might work alone at a remote observatory, recording observations in a notebook, sharing results through papers published months or years later. Now, observations are shared instantly, data is processed collaboratively, and discoveries are announced to the world in real time. The response to Atlas showcased this new paradigm perfectly. Professional observatories adjusted their schedules to observe the comet. Space telescopes, including Hubble, were tasked with taking high-resolution images. Amateur astronomers set up networks to provide continuous coverage as the comet moved across the sky. It was like a global orchestra with thousands of instruments all focused on the same cosmic performance, each contributing their own observations to create a comprehensive picture. But we're not just watching the skies, we're preparing to act. The same period that saw Atlas approach and fragment also saw unprecedented developments in planetary defense. The DART mission, Double Asteroid Redirection Test, was in final preparation for its launch in 2021. This mission would demonstrate humanity's ability to change the orbit of an asteroid by deliberately crashing a spacecraft into it. It's the first time in the history of life on Earth that a species has developed the capability to prevent an asteroid impact, to actively defend against a threat that has caused mass extinctions in the past. Think about the profound nature of this development. For billions of years, life on Earth has been at the mercy of cosmic impacts. The dinosaurs, dominant for over 150 million years, were wiped out by an asteroid they never saw coming. Countless other species have met similar fates. But now, after 4 billion years of evolution, life has finally produced a species capable of detecting and deflecting these threats. We've become Earth's immune system against cosmic infections. The development of this capability hasn't been driven by immediate threat, but by long-term thinking, by the recognition that even low-probability events become certainties given enough time. This kind of forward-looking, probabilistic thinking is relatively new in human culture. For most of our history, we've been reactive, responding to threats as they appear. But now we're becoming proactive, preparing for threats that might not materialize for centuries or millennia. This shift in thinking extends beyond planetary defense to our entire relationship with space. We're not just watching for threats. We're actively exploring, sending robotic emissaries to every major body in the solar system. As Atlas approached, we had spacecraft orbiting Mars, Jupiter, and Saturn. We had rovers on Mars and a probe on its way to Mercury. We had just completed missions to asteroids Bennu and Ryugu, actually collecting samples to bring back to Earth. We were and are in the process of extending human consciousness throughout the solar system. Each of these missions adds to our understanding of the cosmic environment we inhabit. They're like reconnaissance missions, scouting the territory, learning the terrain, identifying resources and hazards. The data they collect doesn't just satisfy scientific curiosity. It provides practical information for humanity's future in space. Where is the water ice that future colonists will need? Which asteroids contain valuable metals? What are the radiation environments around different planets? We're gathering intelligence for a future we can barely imagine but are actively working to create. The Parker Solar Probe, launched in 2018, is literally touching the sun, flying through its corona to understand our star's behaviour. The Voyager probes, launched in 1977, have left the solar system entirely, carrying messages from Earth into interstellar space. These missions represent humanity's first tentative steps toward becoming an interstellar species, extending our presence beyond the confines of our birth system. But perhaps more important than our robotic explorers is the change in human consciousness they represent. We've begun to think of ourselves as a spacefaring species. Even though only a few hundred humans have ever left Earth's surface, this shift in identity, from earthbound to spacebound, is profound. It changes how we see ourselves, our future, and our responsibilities. The emergence of private space companies has accelerated this transformation. SpaceX, Blue Origin, Virgin Galactic, and dozens of other companies are democratizing access to space, reducing costs, and expanding capabilities. What was once the exclusive domain of superpower governments is becoming accessible to companies, universities, even individuals. We're on the verge of a new era of space exploration and exploitation, driven not by Cold War competition, but by commercial opportunity and human ambition. This commercialization of space might seem mundane compared to the grand questions of cosmic intelligence and mysterious comets, but it's actually crucial to our development as a spacefaring species. It provides the economic incentive for developing better technologies, for establishing permanent presence in space. for eventually expanding beyond Earth. If Atlas was indeed monitoring our development, the emergence of commercial spaceflight would be a significant milestone, indicating that we're moving beyond government-sponsored exploration to sustainable space development. The cultural impact of our space activities is equally important. Every image from Mars, every discovery of an exoplanet, every close-up of a comet or asteroid shapes how we see ourselves and our place in the universe. We're raising a generation that takes space exploration for granted, that sees Earth from space every day through satellite imagery, that considers traveling to Mars a realistic career option. This normalization of space is preparing humanity psychologically for a future among the stars. The international nature of space exploration is another crucial development. The International Space Station, despite all the political tensions on Earth, has been continuously occupied for over 2 decades. With astronauts from many nations working together, the Artemis Accords, signed by dozens of countries, establish principles for peaceful lunar exploration. Even as nations compete and conflict on Earth, they cooperate in space, united by the common challenge of surviving and thriving beyond our planet. When Atlas fragmented, observers from dozens of countries contributed data. Chinese telescopes, European space probes, American surveys, Russian observatories, all focused on the same object, sharing information freely. This kind of international cooperation, routine in astronomy, provides a model for how humanity might unite in response to a genuine cosmic threat or opportunity. If the comet was testing our ability to work together, we demonstrated that despite our differences, we can unite when facing the cosmos. The role of amateur astronomers in the Atlas observation campaign deserves special attention. These dedicated individuals, observing from backyards and small observatories, contributed valuable data that complemented professional observations. They provided continuous coverage when professional telescopes were pointed elsewhere, tracked fragments too faint for automated surveys, and brought human intuition and pattern recognition to bear on the problem. This collaboration between professionals and amateurs represents a democratization of astronomy that would have been impossible in earlier eras. The internet has been crucial in enabling this collaboration. Online forums, social media groups, and specialized platforms allow observers to share data instantly, coordinate observations, and collectively analyze results. When Atlas began fragmenting, amateur astronomers worldwide knew about it within hours, not through official channels, but through Twitter, Facebook, and astronomy forums. This rapid, as informal communication network complements official channels and ensures that no important observation is missed. The software tools available to modern astronomers, both professional and amateur, would seem like magic to earlier generations. Programs that can automatically detect moving objects, calculate orbits, predict future positions, and simulate celestial mechanics are freely available. A teenager with a laptop can perform calculations that would have required teams of mathematicians just decades ago. This democratization of computational power has transformed astronomy from an elite pursuit to something accessible to anyone with interest and dedication. But being watchers involves more than just technology. It requires a certain mindset, a combination of patience and vigilance, curiosity and discipline. Astronomers, whether professional or amateur, spend countless hours staring at screens, analyzing data, looking for tiny deviations that might indicate something interesting. It's a kind of meditation, a practice of focused attention that connects us to traditions going back to ancient astronomers who watched the skies with naked eyes. This practice of watching has philosophical implications. By observing the universe, we're not passive recipients of information, but active participants in the cosmic story. Every observation slightly changes the observer, adding to their understanding, shaping their world view. And if we accept the possibility that some cosmic phenomena might be intentional, then observation becomes a form of communication, a dialogue between watcher and watched. The question of who's watching whom becomes particularly interesting in this context. If Atlas was indeed a probe, then as we watched it, it was watching us. Our observations, our response to its fragmentation, our attempts to understand it, all would have provided information about our capabilities and nature. We were simultaneously subject and object, observer and observed, scientist and specimen. This dual role is humbling and empowering at the same time. Humbling because it reminds us that we might be under scrutiny by intelligences far beyond our understanding. Empowering because it means we're significant enough to be worth watching, that our development matters on a cosmic scale. We're not alone and forgotten in the vastness of space, but part of a larger community, even if we haven't yet made formal contact with other members. The pale blue dot that is Earth has developed eyes, and those eyes are looking outward with increasing sophistication and range. We've gone from seeing only what's visible to naked eye to detecting radio waves, infrared radiation, X-rays, gravitational waves. We've extended our vision across the electromagnetic spectrum and beyond, creating new senses that our biological evolution never provided. Each new way of seeing reveals new aspects of the universe, new phenomena to understand, new questions to ask. The recent detection of gravitational waves opens particularly exciting possibilities. These ripples in space-time, predicted by Einstein but not detected until 2015, provide a completely new way of observing the universe. They can pass through matter unimpeded, carrying information from regions opaque to electromagnetic radiation. If advanced civilizations use gravitational waves for communication or propulsion, we've just developed the ability to potentially detect such activities. Similarly, our growing understanding of neutrinos, those ghostly particles that barely interact with matter, might eventually allow us to detect signatures of advanced technology. Neutrinos produced by fusion reactions in stars stream through space, passing through planets as if they weren't there. An advanced civilization might use modulated neutrino beams for communication, knowing that only scientifically sophisticated species could detect them. Our search for biosignatures and exoplanet atmospheres represents another kind of watching. Using spectroscopy, we can analyze the light passing through distant atmospheres, looking for oxygen, methane, and other gases that might indicate life. Soon, we might be able to detect not just biosignatures, but technosignatures, evidence of industrial activity on distant worlds. We're developing the ability to watch not just objects, but entire civilizations, if they exist. But perhaps the most important aspect of being watchers is not what we see, but how seeing changes us. Every discovery expands our perspective, challenges our assumptions, and enriches our understanding. The boy who first saw Saturn's rings through Galileo's telescope was transformed by that vision. The girl who sees the first clear image of an Earth-like exoplanet will be similarly changed. Each generation sees farther and deeper than the last, and each is shaped by what they see. The children growing up today take for granted images from the surface of Mars, close-ups of Pluto, and the discovery of thousands of exoplanets. Their baseline understanding of the universe is radically different from previous generations. They're growing up as citizens of the cosmos, not just Earth. When they look up at the night sky, they don't see distant, unknowable lights, but places we've been or might go, worlds that might harbour life, stars around which other watchers might be looking back. This cosmic perspective is perhaps the greatest gift of our watching. It lifts us above the petty conflicts and narrow concerns that dominate daily life. It reminds us that we're all crew members on the same small spacecraft, sharing the same thin atmosphere, dependent on the same fragile biosphere. The overview effect experienced by astronauts who see Earth from space is gradually being experienced by all of humanity through the images and data our watchers provide. As Atlas approached and fragmented, we demonstrated that we've become competent watchers. We detected it early, tracked it precisely, observed its fragmentation in detail, and analyzed the results thoroughly. We showed that we can coordinate globally, share information freely, and maintain scientific operations even during a pandemic. If it was a test, we passed at least the basic requirements. But being watchers is just the beginning. The next step is becoming actors, not just observing cosmic phenomena, but actively engaging with them. The DART mission is a first step, showing we can change the trajectory of celestial bodies. Future missions might involve capturing asteroids, mining them for resources, or even redirecting comets to provide water for space colonies. We're transitioning from passive observation to active participation in the cosmic dance. This transition carries responsibilities. As we develop the power to affect celestial bodies, we must also develop the wisdom to use that power appropriately. We need ethical frameworks for space activities, international agreements on resource exploitation, and protocols for responding to potential contact with other intelligences. We're not just watching the cosmos, we're preparing to join it as active participants. The watchers on the pale blue dot are evolving rapidly. Each new telescope, each new mission, each new discovery adds to our capabilities and understanding. We're like children learning to see, gradually making sense of the vast, complex, beautiful universe around us. And perhaps, somewhere out there, other watchers are observing our progress with interest, waiting for us to develop enough to join a larger community of cosmic observers. As you lie there in the peaceful darkness, feeling yourself becoming one of the watchers even in rest, remember that every human who looks up at the stars contributes to this collective watching. Professional astronomers with their giant telescopes, amateur observers with their backyard instruments, children with their first pair of binoculars, and you, right now, contemplating these mysteries, all a part of humanity's growing awareness of the cosmos. We are the universe becoming conscious of itself, matter organized into patterns capable of recognizing other patterns, stardust contemplating stars. The pale blue dot has developed eyes, and those eyes are opening wider every day. What we'll see in the coming years and decades is impossible to predict, but one thing is certain, we'll be watching. And perhaps, when the next mysterious visitor like Atlas arrives, we'll be ready not just to observe, but to understand, not just to watch, but to respond, not just to wonder, but to know. The beauty of the unanswered. Here, in the deep quiet of contemplation, we arrive at something profound. The recognition that not knowing, not being certain, not having all the answers is not a failure of science or human understanding, but rather one of its greatest triumphs. Atlas came and went, leaving us with more questions than answers, and perhaps that's exactly as it should be. As you drift there in the darkness, feeling the gentle weight of mystery settling over you like a comfortable blanket, let me share with you why the unanswered questions about Atlas, about cosmic visitors, about our place in the universe are themselves a kind of answer. A gift more valuable than any certainty could be. We live in an age that often mistakes information for wisdom, data for understanding, answers for truth. We've become accustomed to instant responses to our queries, to search engines that provide millions of results in fractions of a second, to the illusion that everything knowable is already known and merely waiting to be looked up. But Atlas reminds us that the universe doesn't operate like a search engine. It doesn't provide neat, packaged answers to our questions. Instead, it offers mysteries wrapped in enigmas, puzzles that lead to deeper puzzles, questions that bloom into gardens of wonder. The mystery of Atlas connects us to one of the deepest and most persistent questions in human thought. Are we alone? This question, simple in its formulation but profound in its implications, has haunted and inspired our species since we first developed the capacity for abstract thought. Every culture has wondered about beings beyond Earth, whether gods, spirits, or other forms of life. Now, in the scientific age, we've refined this wondering into what's known as the Fermi paradox, named after the physicist Enrico Fermi, who famously asked, "Where is everybody?" The paradox is simple but powerful. Given the vast number of stars in our galaxy, the billions of years available for life to develop, and the relative youth of our solar system, we should expect the galaxy to be teeming with advanced civilizations. Some of these civilizations should be millions or billions of years older than ours, with technologies that would seem like magic to us. They should have colonized the galaxy by now, or at least filled it with obviously artificial signals or structures. Yet when we look up, we see no obvious signs of intelligence beyond Earth. The universe appears natural, uninhabited, silent. Many solutions to the Fermi paradox have been proposed. Perhaps life is extraordinarily rare, and we're the only intelligence in our galaxy, or even the observable universe. Perhaps intelligence life is common but doesn't last long, destroying itself through war, environmental collapse, or accidents with advanced technology. Perhaps advanced civilizations choose not to expand or communicate, turning inward to virtual realities or other dimensions. Perhaps they're hiding, bro, afraid of some cosmic threat we're not yet aware of. Or perhaps, as our speculation about Atlas suggests, they're here but camouflaged, watching without interfering, waiting for us to reach some threshold of development. Each proposed solution to the Fermi paradox carries profound implications for humanity's future. If we're alone, then we bear the awesome responsibility of being the only known consciousness in the universe, the only witnesses to cosmic beauty, the only beings capable of understanding and appreciating existence. If intelligence is common but short-lived, then we need to identify and avoid whatever filters destroy civilizations. If advanced beings are hiding or watching, then we need to prepare for eventual contact while continuing our development. The beauty of the Fermi paradox is that it remains genuinely unsolved. Despite decades of searching, despite increasingly sophisticated instruments and methods, we still don't know if we're alone. This uncertainty is not a failure but a success of the scientific method. We've been honest enough to acknowledge our ignorance, rigorous enough to avoid premature conclusions, and imaginative enough to consider multiple possibilities. The unanswered question keeps us searching, thinking, wondering. Atlas adds an interesting footnote to the Fermi paradox. If it was indeed artificial, then the paradox is partially resolved. We're not alone. But contact is subtle, ambiguous, deniable. If it was natural, then it still serves as a reminder of how difficult it is to distinguish between natural and artificial phenomena at cosmic scales. Either way, it enriches our thinking about the paradox and our approach to resolving it. The search for extraterrestrial intelligence has evolved considerably since its inception in the 1960s. Early SETI efforts focused on radio signals, assuming that advanced civilizations would broadcast powerful radio or television signals that we could detect. When we didn't find such signals, we refined our search, looking for laser pulses, infrared excesses from Dyson spheres, or other technosignatures. Each null result has taught us something about what advanced civilizations might or might not do, gradually constraining the possibility space. But perhaps we've been looking for the wrong things in the wrong places. Perhaps advanced civilizations don't announce themselves with obvious signals, but instead communicate through subtle modifications of natural phenomena. A comet trajectory slightly adjusted, a star's spectrum minutely altered, a pattern of supernovae that's not quite random. These signals would be invisible to casual observation, but detectable by sufficiently advanced science. They would maintain cosmic privacy while allowing communication between those capable of recognizing the patterns. This idea transforms how we think about SETI. Instead of just pointing radio telescopes at stars and listening for artificial signals, we should be looking for statistical anomalies in all cosmic phenomena. Are comet orbits more organized than they should be? Do certain stellar spectra show inexplicable patterns? Are there correlations in cosmic events that can't be explained by known physics? This approach requires not just better instruments, but better analysis, more sophisticated pattern recognition, more creative thinking about what constitutes a signal. The beauty of this expanded search is that it makes every astronomical observation potentially relevant to SETI. Every comet studied, every star analyzed, every galaxy surveyed might contain clues to cosmic intelligence. We're not just doing astronomy, we're potentially doing archaeology, looking for artifacts and influences of ancient civilizations. The entire universe becomes a potential message board, a gallery of possibly intentional art, a library of encoded information. But even if we never find definitive evidence of extraterrestrial intelligence, the search itself is valuable. It forces us to think about intelligence, consciousness, and communication in the broadest possible terms. It challenges our assumptions about what's natural and what's artificial. It expands our imagination about possible forms of life and mind. It connects us to the cosmos in a deeply personal way, making us active participants in a cosmic community, even if we're currently the only known members. The unanswered questions about Atlas specifically teach us about the limits and possibilities of our knowledge. We know its orbit precisely, its composition approximately, its fragmentation pattern in detail. But we don't know, and may never know, whether its behavior was entirely natural or partially designed. This uncertainty is frustrating for those who want definitive answers, but it's exhilarating for those who appreciate mystery. Living with uncertainty is a crucial skill, both scientifically and personally. The universe doesn't owe us closure. Many questions we ask may not have answers, or at least not answers accessible to us with our current understanding and technology. Learning to be comfortable with this uncertainty, to find beauty in the unknown, to continue searching without guaranteeing success, these are marks of intellectual and emotional maturity. The mystery of Atlas also connects us to the long tradition of cosmic wonder that defines our species. From ancient astronomers tracking the paths of planets, to modern scientists detecting gravitational waves, humans have always been drawn to celestial mysteries. Each generation has its own unanswered questions, its own cosmic puzzles. The questions change as our knowledge grows, but the sense of wonder remains constant. Think about how our cosmic questions have evolved. Ancient humans wondered what the lights in the sky were. Once we understood they were stars and planets, we wondered how they moved. Once we understood their motions, we wondered what they were made of. Once we understood their composition, we wondered how they formed and evolved. Now we wonder if any harbour life, if any have produced intelligence, if any have sent probes to Earth disguised as comets. Each answered question has led to deeper questions, an infinite regress of wonder. This progression suggests that our current mysteries, including Atlas, are not endpoints but waypoints. Future generations will likely look back at our speculation about Atlas with the same mixture of appreciation and amusement that we feel toward ancient theories about comets being atmospheric phenomena or harbingers of doom. They'll have new data, new theories, new mysteries. The specific questions will change, but the questioning itself will continue. The unanswered nature of Atlas also protects it from becoming mundane. If we knew for certain that it was just a normal comet, it would be catalogued and largely forgotten, another data point in our growing database of solar system objects. If we knew for certain it was an alien probe, it would be sensational initially, but would eventually become just another fact absorbed into our worldview. But because we don't know, can't know with current data, it remains forever interesting, forever mysterious, forever capable of inspiring wonder and speculation. This preservation of mystery is important for human psychology and culture. We need unknowns to explore, frontiers to cross, questions to pursue. A universe with all questions answered would be a kind of prison, offering no room for growth, discovery, or surprise. The unanswered questions are what keep us moving forward, developing new instruments, new theories, new ways of seeing. They're the engine of scientific progress and human development. The beauty of unanswered questions extends beyond science to philosophy and meaning. Why does the universe exist? Why is there something rather than nothing? What is consciousness? What is our purpose? These questions may not have answers, or at least not answers that human minds can comprehend. But the asking itself is meaningful. It connects us to every human who has ever wondered about existence, creating a continuity of questioning that spans cultures and millennia. Atlas, in its ambiguity, becomes a mirror for these deeper questions. When we ask whether it was designed, we're really asking whether the universe contains purpose and intention beyond human consciousness. When we wonder if it was watching us, we're wondering if we matter on a cosmic scale. When we speculate about its message, we're hoping that existence itself has meaning that we can discover and understand. The fact that we can ask these questions, that we have minds capable of contemplating cosmic mysteries, is itself a profound answer to questions we haven't quite learned how to ask. We are matter organized in such a way that it can wonder about itself. We are the universe developing the capacity for self-reflection. We are stardust that has learned to study stars. This is either an almost impossible accident or a fundamental feature of cosmic evolution, and either possibility is awe-inspiring. The community of wonder that forms around mysteries like Atlas is another beautiful aspect of unanswered questions. Scientists, amateur astronomers, science fiction writers, philosophers, and curious individuals from all walks of life can come together in shared speculation. The mystery becomes a meeting ground where different perspectives and ways of knowing can interact. The poet's metaphor might inspire the scientist's hypothesis. The philosopher's question might guide the engineer's design. The child's imagination might reveal possibilities the expert overlooked. This democratization of wonder is particularly important in our increasingly specialized world. Most scientific questions have become so technical that only experts can meaningfully engage with them. But cosmic mysteries like Atlas remain accessible to anyone willing to look up and wonder. You don't need a PhD to ask whether we're alone in the universe, or to imagine what an alien probe might look like. These questions belong to all of humanity, connecting us across educational, cultural, and economic boundaries. The unanswered questions about Atlas also teach us humility. Despite our sophisticated instruments and theories, despite our growing understanding of physics and chemistry, despite our ability to model and predict many cosmic phenomena, we still can't definitively say whether a comet that passed through our solar system was natural or artificial. This humility is healthy. It reminds us that we're still young as a scientific civilization, still learning to read the cosmic signs, still developing the tools and concepts we need to understand our universe. But this humility is balanced by pride in what we have accomplished. We detected Atlas when it was still far from the Sun. We calculated its orbit precisely. We observed its fragmentation in unprecedented detail. We analyzed its composition and dynamics. We asked sophisticated questions about its nature and origin. Even if we can't answer all these questions, the fact that we can ask them represents an extraordinary achievement for a species that only invented the telescope 4 centuries ago. The tension between what we know and what we don't know, between our achievements and our limitations, between answers and questions, is where science lives and thrives. It's the creative tension that drives discovery. If we knew everything, there would be no science. If we knew nothing, there could be no science. It's precisely because we know enough to ask meaningful questions, but not enough to answer them all that science is possible and necessary. As we contemplate the beauty of unanswered questions, it's worth remembering that some of today's mysteries will be tomorrow's knowledge. Future generations may look back at our speculation about Atlas with the benefit of additional data and understanding. They may discover other fragments of the same parent body that reveal its true nature. They may develop new theories that explain its fragmentation pattern. They may even make contact with extraterrestrial intelligence and learn that Atlas was indeed a probe or definitely wasn't. But even as some questions are answered, new ones will arise. The frontier of mystery will move but never disappear. Each generation will have its own Atlas, its own cosmic enigma that captures imagination and drives investigation. The specific mysteries change, but mystery itself is eternal, as fundamental to the universe as matter and energy. The beauty of the unanswered also lies in its invitation to participate. Every person who thinks about Atlas, who imagines possibilities, who asks, "What if?" becomes part of the ongoing human endeavour to understand the cosmos. You don't need to be a professional scientist to contribute to this endeavour. Sometimes the most important contributions come from outsiders who see patterns that experts miss, who ask questions that haven't been asked, who imagine possibilities that haven't been considered. So as you lie there in the darkness, drifting towards sleep, carry with you the beauty of not knowing. Let the mystery of Atlas, the question of whether we're alone, the wonder of existence itself settle into your consciousness not as problems to be solved, but as invitations to wonder. The universe doesn't require us to have all the answers. It only asks that we keep questioning, keep searching, keep marvelling at the magnificent mystery of it all. The unanswered questions are not failures or frustrations, but gifts. They ensure that no matter how much we learn, there will always be more to discover. They guarantee that future generations will have their own frontiers to explore, their own mysteries to contemplate. They keep the universe interesting, keep us growing, keep the adventure of consciousness moving forward into the unknown. And perhaps that's the most beautiful answer of all, that there will always be unanswered questions, always be mysteries to explore, always be reasons to look up at the night sky with wonder. Atlas may be gone, its fragments dispersed, its nature forever uncertain, but the questions it raised will ripple through human consciousness for generations to come, inspiring new searches, new theories, new ways of seeing our place in the cosmic dance, drifting into the cosmos. And now, dear traveller, we come to the end of our journey, though in truth there are no endings in the cosmos, only transformations, only continuations in new forms. As you lie there, feeling the gentle pull of sleep beginning to claim your consciousness, let us take these last moments together to weave all we've discussed into a final meditation, a peaceful contemplation of our place in the vast, mysterious, beautiful universe that Atlas briefly illuminated with its presence. The comet is gone, its dust scattered, its fragments invisible, but what it represented, what it made us think and feel and wonder, that remains, settling into our collective memory like stardust settling onto a quiet world. The story of Atlas is really our story, isn't it? A story of beings who emerged from cosmic dust, evolved consciousness from mere matter, and developed the capability to observe and question the very cosmos that created us. When we watched Atlas approach, brighten, fragment, and fade, we were watching a kind of cosmic mirror, seeing ourselves reflected in the ice and dust of an ancient wanderer. Every observation we made, every question we asked, every speculation we entertained, revealed as much about us as it did about the comet. Think about where we are right now at this exact moment in cosmic history. The universe is 13.8 billion years old, and we exist in this particular instant conscious and aware, capable of contemplating that vast span of time. The atoms in your body, the carbon in your muscles, the iron in your blood, the calcium in your bones, were forged in the hearts of dying stars billions of years ago. You are literally made of cosmic material, organized temporarily into a pattern capable of recognizing its own cosmic nature. When you look at a comet, you're stardust observing stardust, the universe examining itself. This perspective transforms everything. The questions about whether Atlas was natural or artificial, whether we're alone or watched, whether the universe contains purpose or merely process, these become questions the universe is asking about itself through us. We are the cosmos developing self-awareness, matter achieving consciousness, time contemplating eternity. The mystery of Atlas is the universe mysterious to itself, wondering about its own nature through billions of human minds. As you drift towards sleep, feeling your breathing slow and deepen, imagine yourself not as separate from the cosmos but as part of it, a temporary concentration of cosmic awareness in the vast flow of matter and energy. Your thoughts about Atlas, your wonderings about alien intelligence, your contemplation of cosmic mysteries, These are not small, insignificant mental events, but part of the universe's growing self-understanding. Every human who has ever looked up at a comet and wondered has contributed to this cosmic consciousness. The fragments of Atlas continue their journey through the solar system as we rest. Right now, at this very moment, they're out there in the darkness between the planets, following their modified orbits, carrying with them the memory of their shared origin and violent separation. Some are probably still outgassing slightly, releasing the last of their volatile materials in wisps too faint for our instruments to detect. Others have gone completely dark, inactive chunks of rock and ice tumbling through the void. In a few years, or decades, or centuries, one of these fragments might brighten again as it approaches the sun, appearing as a new comet to future observers who may not even know its connection to Atlas. They'll track it, analyze it, wonder about it, just as we wondered about Atlas. The cycle of observation and mystery will continue, each generation adding their own chapter to the ongoing story of humanity's relationship with the cosmos. But the physical fragments are only part of Atlas's legacy. The data collected during its passage, the thousands of images, the hundreds of spectra, the precise measurements of its position and brightness, all of this information is preserved in digital archives around the world. Future scientists with better theories and more sophisticated analysis techniques will revisit this data, possibly finding patterns we missed, answering questions we couldn't answer, or asking new questions we haven't thought to ask. This is one of the beautiful aspects of modern astronomy. Data is immortal. The photons that left Atlas and struck our detectors in 2020 are preserved as patterns of ones and zeros that can be analysed and reanalyzed indefinitely. In a sense, we've captured a moment of cosmic time, frozen it in our databases, made it permanently accessible to human consciousness. Centuries from now, when all of us who watched Atlas are long gone, the comet will still exist in our data, still capable of teaching and inspiring. The questions Atlas raised about extraterrestrial intelligence, about natural versus artificial, about watching and being watched, these questions have become part of human culture. They've been discussed in scientific papers and coffee shops, in classrooms and online forums, in this very conversation we're having now as you drift toward dreams. Each discussion spreads the questions further, plants seeds of wonder in new minds, ensures that the mystery continues to propagate through human consciousness, and perhaps that propagation is itself a kind of answer. Whether or not Atlas was designed to make us think, it has made us think. Whether or not it was intended to test our capabilities, it has tested them. Whether or not it carried a message, it has become a message, a reminder of our cosmic context, our technological achievements, our enduring mysteries. The comet has become what we needed it to be: a mirror, a teacher, a source of wonder. As sleep approaches, let your mind drift like those fragments of Atlas, following its own trajectory through the space of consciousness. You don't need to hold on to any particular thought or maintain any specific focus. Just let yourself float in the awareness that you are part of something vast and mysterious and beautiful. You are cosmic matter that has temporarily achieved the remarkable state of being able to contemplate itself and its origins. The bedroom around you, the building you're in, the city or countryside beyond, the planet Earth itself, all of it is drifting through space just as surely as Atlas was. We're all cosmic travellers, riding this pale blue dot on its journey around the sun, which itself orbits the galactic centre, which itself moves through the expanding universe. The feeling of stillness you experience lying in bed is an illusion. You're moving at tremendous speeds through multiple frames of reference. A cosmic dancer participating in the grand ballet of celestial mechanics. This movement connects you to Atlas and every other cosmic body. You're following the same laws of physics, responding to the same fundamental forces, participating in the same cosmic evolution. The difference is that you're aware of it. You can contemplate your journey, wonder about your destination, imagine other travellers in the vast darkness. This awareness is either the universe's greatest accident or its fundamental purpose, and both possibilities are equally magnificent. The silence of space that surrounded Atlas surrounds us too, just beyond our thin atmosphere. If you could somehow turn off all the sounds of Earth, the wind and waves, the animals and machines, the constant hum of human activity, you'd hear the same profound silence that accompanies every comet on its journey. It's not an empty silence, but a pregnant one, full of potential, waiting for consciousness to fill it with meaning. In that silence, questions echo without answers, and that's perfectly fine. Did Atlas carry a message we couldn't decode? Are we being watched by intelligence beyond our understanding? Are comets sometimes probes? Asteroids occasionally artifacts? Meteors potentially messages? The silence doesn't answer, but it doesn't deny either. It holds all possibilities in quantum superposition, waiting for future observations to collapse the wave function of uncertainty into knowledge. But even when we achieve knowledge, mystery remains. Every answered question reveals new questions, like a fractal pattern of wonder that maintains its complexity no matter how deeply we zoom in. We might someday know for certain whether Atlas was natural or artificial, but that answer will only lead to new mysteries. If natural, how did nature produce such an unusual fragmentation? If artificial, who sent it and why? The journey of questioning never ends, and that's the beauty of it. You are part of this eternal questioning, this cosmic curiosity that might be the universe's way of understanding itself. Every time you wonder about something, whether it's the nature of a comet or the meaning of existence, you're participating in the universe's self-examination. Your thoughts, however small they might seem, are part of the cosmic process of awareness emerging from matter, meaning crystallizing from chaos. The children who will grow up in a world where Atlas is history, rather than news, will have their own cosmic mysteries to contemplate. Perhaps they'll witness the arrival of another unusual comet, or the discovery of definitive biosignatures on an exoplanet, or even first contact with extraterrestrial intelligence. Each generation inherits the questions of previous generations and adds their own, building an ever-growing edifice of wonder. But you don't need to wait for future mysteries. Right now, as you drift towards sleep, you're surrounded by cosmic enigmas. Dark matter permeates the space around you, its nature still unknown despite decades of searching. Dark energy drives the expansion of the universe through mechanisms we don't understand. Quantum mechanics and general relativity remain unreconciled, suggesting our fundamental theories are incomplete. Consciousness itself, the very awareness you're experiencing right now, remains largely unexplained by science. These mysteries aren't problems to be solved tonight. They're invitations to wonder, to imagine, to dream. As sleep takes you, let your mind play with possibilities. Perhaps in your dreams you'll follow Atlas on its journey, see through its icy eyes, understand its true nature. Perhaps you'll communicate with the intelligence that might have sent it, or discover that the intelligence was in the comet itself, a kind of consciousness we haven't yet learned to recognize. Dreams are where impossible possibilities become temporarily real, where the boundaries between self and cosmos dissolve. The room around you is quiet now, but it's the quiet of potential, like the space between notes in a cosmic symphony. Atlas was one note in that symphony, a brief tone that rose and fell, leaving us to wonder about the composition it was part of. We may never hear the full symphony, but we can appreciate the notes we do hear, the fragments of cosmic music that reach our ears and instruments. As your consciousness begins to fade into sleep, remember that this fading is temporary. You'll wake tomorrow, and the universe will still be there, full of mysteries and wonders, comets and questions, beauty and uncertainty. Atlas may be gone, but other cosmic visitors will come. Some might be natural, products of the same forces that shaped our solar system. Others might be something else, carrying messages we're not yet equipped to read, running tests we don't know we're taking, watching us with senses we can't imagine. But whether natural or artificial, whether alone or observed, whether meaningful or random, will keep watching. We'll keep wondering. We'll keep reaching out with our instruments and our imaginations, trying to understand our place in the cosmic order. It's what we do. It's who we are. We're the watchers on the pale blue dot, the questioners in the cosmic silence, the brief flames of consciousness in the vast darkness. The story of Atlas is ending for now, but your story continues. Tomorrow you'll wake with a memory of this journey we've taken together, this exploration of cosmic possibilities. Perhaps you'll look at the sky differently, wondering what might be approaching unseen. Perhaps you'll think about the fragments still drifting out there, carrying their secrets through the darkness. Perhaps you'll simply carry with you a deeper appreciation for the magnificent mystery of existence. Let sleep take you now, as gently as Atlas faded from our instruments. Let your consciousness disperse like comet fragments, each thought drifting on its own trajectory through the space of dreams. You don't need to hold on to anything. You don't need to understand everything. You just need to be, to rest, to exist as part of the cosmic whole. The universe continues its expansion as you sleep. Galaxies drift apart, stars are born and die, comets fall from the Oort cloud, planets spin in their orbits. And on one small planet, orbiting an ordinary star, in an unremarkable galaxy, conscious beings sleep and dream, adding their small but significant contribution to the universe's growing self-awareness. You are one of those beings, cosmic matter temporarily blessed with consciousness, stardust given the gift of wonder. As you drift into dreams, you carry with you billions of years of cosmic evolution, the legacy of countless stars that lived and died to create the atoms of your body. You are the universe dreaming of itself, and in your dreams, perhaps you'll glimpse truths that waking consciousness can't quite grasp. Atlas is gone, but its questions remain, floating in the darkness like fragments of light, waiting for future observers to gather them, examine them, and add their own questions to the cosmic collection. The mystery continues. The wonder endures. The universe keeps its secrets while slowly, patiently, lovingly revealing itself to those who watch and wait and dream. Sleep now, cosmic traveler. Rest in the knowledge that you are part of something magnificent, mysterious, and ongoing. The stars wheel overhead, indifferent and intimate. Comets continue their ancient journeys, and somewhere in the vast darkness, perhaps something watches, waits, and wonders about us just as we wonder about it. The cosmos embraces you as you drift into dreams, another mote of consciousness in the infinite night, another questioner in the eternal mystery, another fragment of the universe contemplating itself. Rest well, knowing that tomorrow the questions will remain, the wonder will continue, and the cosmic journey will carry on, with you as part of it, forever and always, until the last star fades, and perhaps even beyond, into mysteries we haven't yet imagined. Good night, fellow traveler. May your dreams be filled with cosmic wonders, and may you wake refreshed and ready to continue the eternal human quest to understand our place in the magnificent, mysterious cosmos that Atlas reminded us we're part of. The comet may be gone, but we remain, carrying its questions forward into the future, adding our own chapter to the never-ending story of consciousness engaging with the cosmos. And in the silence and darkness, the universe continues its patient unfolding, keeping its secrets, revealing its wonders, inviting us always deeper into the beautiful mystery of existence.